Hello there and welcome to Just About Earth, where curiosity gets comfortable and science takes its time. Tonight we're easing into a story that begins very far from our planet and ends in a place that feels almost impossible to imagine. A world quietly thriving beneath ancient seas, unaware that something unimaginably violent may have already been on its way. It is the kind of story that sounds as though it belongs in speculative fiction, tucked somewhere between cosmic horror and natural history, except this one may have happened for real. Long before people, before dinosaurs, before forests full of bird song or mammals hiding in the undergrowth, Earth may have faced a danger so remote and so powerful that the sky itself became part of the disaster. That danger, if the idea is correct, did not arrive as a crashing asteroid or a curtain of lava or some visible monster rising over the horizon. It did not give the planet a dramatic warning. No mountain split open. No giant wave announced itself from the edge of the sea. Instead, the threat may have come as a beam of radiation from a dying star, or perhaps from two strange, collapsed stellar corpses colliding somewhere in the galaxy, sending out a burst of energy so intense that even across enormous distances it could alter the chemistry of an atmosphere and set off a chain of damage that life on Earth would feel for ages. It is a deeply unfair sort of catastrophe, really. Imagine minding your own business in a shallow Ordovician sea, being a perfectly respectable trilobite or brachiopod, and then finding that the universe has decided to interfere from several thousand light years away. Before we settle into that possibility, I'd love to know where in the world you're listening from tonight. Are you winding down at the end of a long day, sitting in a dim room with a lamp on somewhere in the corner? Is it late where you are, or has your evening only just begun? Perhaps the sky outside is cloudy and close, or perhaps it is one of those clear nights that makes you want to stare upward a little longer than usual, even though the stars can be quite rude if you think about them too carefully. There is something oddly intimate about listening to a story like this while being tucked safely beneath the very atmosphere that protects us now, especially when the story itself is about what can happen when that protection begins to fail. And if you find this sort of slow scientific wandering soothing, interesting, or simply a pleasant way to let your thoughts loosen their grip for a while, I'd be very grateful if you gave the video a like and maybe subscribed as well. It helps this quiet little corner reach other people who might enjoy drifting off to tales of ancient extinctions, atmospheric chemistry, and cosmic events of almost offensive scale. A very niche bedtime routine perhaps, but we all have our comforts. Now this is one of those topics where the size of the idea can arrive before the meaning of it does. A gamma-ray burst sounds dramatic because it is dramatic, but the words themselves do not immediately tell you what kind of thing we're dealing with. It is easy to hear the phrase and imagine some kind of glowing explosion, as though the sky briefly lights up and then everything goes wrong in a very cinematic way. The truth, as usual, is both less theatrical to look at and much more disturbing to understand. Gamma rays are not the sort of thing you would see streaking overhead with a villainous soundtrack. They are an extremely energetic form of electromagnetic radiation, and when they come in a burst from deep space, they can carry more energy in a few moments than our sun will emit over its entire lifetime. That sentence is so unreasonable that it almost sounds like it should be disallowed. Nature, however, has never shown much concern for what sounds fair. What makes this particular story so unsettling is that the Earth did not need to be directly hit like a target in a shooting gallery in the everyday sense. No crater would be required. No impact debris would have to rain down. If a powerful enough burst were aimed our way from a sufficiently close distance, the atmosphere itself could become the casualty first. And if the atmosphere changes, life changes with it. The most immediate victim would likely be the ozone layer, that thin, high-altitude shield that quietly absorbs much of the sun's harmful ultraviolet radiation. We tend not to think of ozone with much affection, which is unfortunate because it does a remarkable job. It sits there in the upper atmosphere, asking for very little recognition, intercepting radiation that would otherwise do severe damage to living tissue. When it is weakened, the surface of the planet becomes a much harsher place. This is where our story reaches back into the Ordovician period, roughly 485 to 444 million years ago, when life on Earth was still mostly marine. There were no birds crossing the sky because there were no birds, no grasslands, no flowering plants, no mammals, no human beings inventing telescopes and then becoming anxious about what they discovered with them. Much of the action of life was happening in the oceans, especially in shallow continental seas. These waters were full of organisms that to modern eyes can seem both alien and oddly charming. Trilobites scuttled about in extraordinary variety: brachiopods, bryozoans, crinoids, and other marine creatures filled ecological roles in a world that was rich, active, and in many places flourishing. It was, by the standards of the time, a success story. Then came one of the largest mass extinctions in Earth's history. The end Ordovician extinction is usually discussed in terms of climate, sea level change, and glaciation, and those remain central explanations. Enormous ice sheets appear to have expanded, sea levels dropped, shallow marine habitats were disrupted, and many lineages were hit hard. That much is well established. But over the years, some researchers have asked whether another factor may have helped trigger or intensify the crisis, especially one capable of rapidly damaging the atmosphere and leaving relatively little obvious geological debris behind. Enter the gamma-ray burst hypothesis, one of the more striking attempts to connect an ancient biological catastrophe with an astrophysical event. It is, I should say at the outset, not a settled certainty. This is not one of those cases where science has unanimously wrapped things up with a tidy bow and moved on. It is a serious idea that has been explored in the literature, modelled in terms of atmospheric effects, and discussed as a plausible mechanism, but it remains a hypothesis. That makes it interesting rather than weak. Science is full of possibilities that must earn their place through evidence, comparison, and repeated challenge. Sometimes an idea survives and becomes part of the standard picture. Sometimes it remains an elegant maybe. Sometimes it turns out to be wrong in a useful way, having forced people to ask better questions. In this case, what makes the hypothesis so compelling is not just the spectacle of the event, but the way it fits a certain kind of damage pattern. A gamma-ray burst would not need to leave a crater. It would not need to announce itself in rocks with obvious fragments of extraterrestrial material. Its fingerprints would be more indirect, written in atmospheric chemistry, ecological stress, and the selective harm done to life exposed to enhanced ultraviolet radiation. There is also something faintly humbling in the idea that Earth's biological history might, at times, have depended not only on what happened within its own systems, but on events unfolding in the wider galaxy. We are used to thinking of extinctions in local planetary terms. Volcanoes erupt, continents shift, oceans circulate differently, an asteroid strikes. All of that is true, and all of it matters enormously. But the universe is not neatly divided into Earth things and space things. The planet sits inside a cosmic environment. Most of the time, that environment is quiet enough, or at least quiet enough by the standards of a species that becomes alarmed when the Wi-Fi takes a moment to reconnect. Yet on long enough timescales and with enough distance covered, the galaxy can become relevant in very direct ways. A star does not have to visit us physically to ruin the mood. That, perhaps, is the strangest emotional feature of this story. It combines remoteness with consequence. If a gamma-ray burst played a role in the Ordovician extinction, then life on Earth was affected by an event so distant that no organism at the time could possibly have understood it, sensed it in any meaningful way, or responded to it as a single obvious threat. There would have been no warning in any conscious sense. The victims of such a process would simply find their world becoming harder to survive in. Sunlight, which had always been a condition of life, would become more damaging. Surface waters would turn more hazardous. Food webs would strain. Species already adapted to particular ranges of depth, temperature and light might begin to fail. The crisis, in other words, would not necessarily look like one dramatic instant followed by silence. It could unfold as a series of worsening consequences, all because the atmosphere had been kicked out of balance by something unimaginably far away. And that is one reason this topic fits so strangely well into a slow evening reflection. It is frightening, yes, but not in the ordinary way. It is not the fear of a predator or a storm or a visible threat moving toward you. It is the discomfort of scale, the discomfort of learning that life on Earth, for all its resilience, has always existed inside systems larger than itself, and that sometimes the larger system behaves with total indifference. It reminds us that safety is often a layered thing. We are protected by distance, by probability, by the structure of our atmosphere, by the orientation of celestial events that have nothing to do with us. We are not merely alive because life is stubborn, though it is. We are also alive because the universe, at least lately, has not chosen to be especially inconvenient. That sentence may sound more flippant than the subject deserves, but a small amount of dry humour is one of the better ways to handle cosmic menace. Otherwise, one risks sounding as though one is whispering dreadful truths from behind a telescope in a candlelit observatory, and that becomes exhausting for everyone. Better, I think, to keep the scale honest and the tone steady. The facts are dramatic enough. Somewhere in the universe, stars do explode in ways that release astonishing torrents of energy. Compact remnants do collide. Radiation does cross interstellar space. Atmospheres do respond to incoming energy. Ozone can be depleted. Ultraviolet radiation can damage DNA. Ecosystems can collapse under pressures that begin in chemistry and unfold through biology. None of that requires theatrical embellishment. It only requires patience to follow the chain, and that chain is what we will be doing as we continue. We will begin with the ancient Earth itself, because before we can understand what may have been threatened, we need to understand what kind of world existed during the Ordovician. It was not merely an empty stage waiting for disaster. It was a crowded, dynamic marine planet with its own geography, climate, seas, and evolutionary experiments already underway. The life of that time matters not just because it suffered, but because it tells us what the world was like before any catastrophe unfolded. You cannot appreciate an extinction properly without first meeting, however briefly, the living world that is about to be interrupted. From there, we will look more closely at gamma ray bursts themselves, what they are, how they form, and why astronomers take them so seriously. These are not rare in the sense of being mythical. They are observed phenomena among the most energetic events known in the universe. The question is not whether gamma ray bursts exist, but under what conditions one could affect a planet like ours. Distance matters, direction matters, duration matters, the atmosphere matters. It is a story of thresholds and probabilities, not one of vague cosmic doom hanging overhead at all times. The universe is dangerous, yes, but thankfully it is also very large, and large spaces are often the only reason anybody gets any sleep. Later, we will move into the atmospheric consequences, because this is where the hypothesis becomes especially concrete. A gamma ray burst interacting with Earth's atmosphere would not simply heat things up in a generic way. It would trigger chemical reactions, particularly involving nitrogen and oxygen, producing compounds that can eat away at ozone. Once ozone is reduced, ultraviolet radiation from the sun increases at the surface. That means the real biological assault may come not from the burst directly, but from the changed relationship between Earth and its own star afterward. There is something bleakly efficient about that. Space hurls a problem at the atmosphere. The atmosphere loses some of its protective structure, and then sunlight takes over the work of injury. After that, the biological consequences begin to come into focus. The shallow seas of the Ordovician would have been especially vulnerable in many respects. Organisms living near the surface, larvae drifting in sunlit water, entire food webs dependent on primary productivity and stable environmental conditions could face profound disruption. Extinctions are not only about creatures suddenly vanishing, they are about systems unravelling. Predators lose prey. Reproductive cycles fail. Habitats contract. ecological relationships that took millions of years to assemble can come apart with surprising speed once enough pressure is applied in the right places. Life is resilient, certainly, but resilience should never be mistaken for invincibility. And then there is the matter of evidence, which gives this whole discussion its scientific backbone. How do you investigate a catastrophe that no human saw, involving a possible cause that leaves behind no smoking gun in the ordinary sense? You compare extinction patterns, you model atmospheric chemistry, you study isotopes, sea levels, glaciation records, and fossil distributions. You ask whether the damage seen in the rocks is compatible with enhanced ultraviolet stress. You examine whether other explanations already account for the observed facts, or whether something additional is needed. In other words, you proceed with caution, which is perhaps less flashy than announcing that a death beam from space nearly sterilized the planet, but considerably more useful. For now, though, it is enough to sit with the basic premise and let its scale settle. Hundreds of millions of years ago, in an ocean world busy with strange marine life, Earth may have been brushed by one of the most violent phenomena the universe can produce. Not struck by stone, but altered by radiation. Not shattered outright, but pushed toward biological crisis through the weakening of the atmosphere above it. It is the kind of story that asks us to keep several sizes of reality in mind at once. The microscopic vulnerability of living tissue, the planetary fragility of atmospheric balance, and the galactic violence of stars ending badly. So as we continue, let your thoughts ease into that older world for a while. Picture the Ordovician seas not as a prelude to us, but as a real present of their own, full of organisms getting on with life under a sky they could not question. The continents were arranged differently. The oceans held communities unlike those of today. The land was still mostly bare, and above it all, beyond the blue air and the sunlight and the ordinary turning of the planet, the rest of the galaxy went on doing what it does, quietly preparing events that no trilobite, no reef-dwelling colony, no drifting lava could ever have imagined. There is something especially unsettling about dangers that do not travel toward you in any familiar sense. A storm has a front, a wildfire has smoke, even an asteroid, at least in principle, is an object moving through space, a physical intruder with weight and trajectory and the decency to be made of matter. But a gamma-ray burst is different. It does not arrive like a rock thrown across a room. It arrives as radiation, as an enormous release of energy moving at the speed of light. And if a planet happens to be in the wrong place at the wrong time, the consequences begin before anything living there could possibly understand that something has happened. It is less like being struck by an enemy, and more like waking to find that the rules governing your environment have quietly changed overnight. If the Ordovician gamma-ray burst hypothesis is correct, then Earth once occupied exactly that wrong place. Not in some melodramatic centre of the crosshairs way, as though the cosmos had formed a personal grudge against marine invertebrates, but through geometry, probability, and bad luck. Somewhere in the galaxy, an event of astonishing violence may have released a narrow, intense beam of gamma radiation. Earth may have fallen within that beam, and in a very real sense that was enough. The universe did not need to throw debris at us. It did not need to come closer. It did not even need to be visible in any ordinary way. It only needed to line up. The phrase, "the night the universe aimed at Earth," is, of course, a human way of putting it. The universe does not aim. It has no intention, no decision-making process, no pause in which it considers whether ancient oceans deserve a quiet evening. Still, our language reaches for agency when scale becomes too large to handle comfortably. We say a storm attacks the coast. We say the sun rises. We say the sky threatens rain. None of these are literally true, and yet each expresses something emotionally recognizable. In the same way, to say that the universe aimed at Earth is not to assign motive to a distant stellar catastrophe. It is to acknowledge the unnerving neatness of alignment. A beam formed somewhere unimaginably far away. Our planet happened to sit in its path. Physics did the rest. To understand why that possibility is taken seriously, it helps to linger for a while on what gamma rays actually are. We tend to sort radiation into familiar and unfamiliar categories according to whether it feels useful, dangerous, or pleasantly invisible. Radio waves seem harmless because they carry music and weather forecasts. Microwaves heat leftovers and occasionally betray us by leaving one corner of the pasta cold. Visible light, for obvious reasons, gets very good public relations. Gamma rays, however, occupy the far energetic end of the electromagnetic spectrum. They are not a separate spooky substance. They are the same broad family of phenomena as visible light, just vastly more energetic, and that additional energy is exactly what makes them so damaging. When gamma rays interact with matter, they can ionize atoms, break chemical bonds, and initiate cascades of reactions that ordinary sunlight does not. Most of the time, Earth's atmosphere does an excellent job of shielding the surface from the worst of this sort of incoming radiation. That protective function is easy to overlook because on a good day, the atmosphere feels like almost nothing at all. It is simply there. You walk through it, breathe it, complain about its humidity, and think no further. Yet it is one of the most delicate and important buffers in the history of life. A planet without atmospheric shielding is a much harsher proposition. Too little protection, and radiation becomes a constant biological problem. Too much change in atmospheric chemistry, and life pays for it in other ways. The atmosphere is not just air in the casual sense. It is structure, filter, moderator, and guardian. Which is why any event capable of disrupting it from afar deserves our full attention. A gamma ray burst is one such event, and among the more dramatic ones known to astronomy. These bursts are short-lived, but their power is extraordinary. For a brief time, they can outshine entire galaxies in gamma radiation. That sounds like the sort of sentence science fiction writers compose while grinning in a dark room, but astronomy has had to accept it as fact. Since their discovery in the late 20th century, gamma-ray bursts have become a major topic of study because they represent extremes of energy release that push our understanding of stellar death, compact objects, and high-energy astrophysics. They are not one single simple thing either. Some are associated with the collapse of massive stars, where a rapidly spinning core falls inward and powers relativistic jets. Others are linked to the merger of neutron stars, the dense leftovers of long-dead stars colliding in a way that releases colossal energy and, incidentally, helps produce heavy elements such as gold, which means that somewhere between the beauty of a wedding ring and the possibility of ancient atmospheric devastation lies the same cosmic workshop. Nature really does insist on range. These bursts are also directional, and that matters enormously. The energy is often channeled into jets rather than sprayed uniformly in all directions. This makes the event both more threatening and less likely to affect a given target. More threatening because if you're inside the beam, the intensity is much greater than if the same energy was spread across the whole sky. Less likely because most directions are simply missed. A gamma-ray burst does not menace every planet within some great spherical shell equally. It creates narrow zones of particular danger. So the question is never just how powerful the burst was, but whether its beam intersected your world. In that sense, cosmic disaster has something in common with standing under the one leak in a perfectly large ceiling. There may be plenty of ceiling, but your timing can still be terrible. Now imagine Earth during the Ordovician, long before vertebrates walked on land, long before trees transformed continents, long before anything resembling us had emerged to gaze upward and draw anxious conclusions. The planet was full of life, but mostly marine life. Vast shallow seas spread over continental shelves, and those seas hosted a great diversification of organisms. Trilobites, brachiopods, graptolites, crinoids, and many other forms were living in ecologies that had become rich and elaborate. This was not some primitive trial run barely worth mentioning before more famous ages arrived. The Ordovician biosphere was complex, productive, and globally important. It was one of the major chapters in the history of life, full of innovation and expansion. If a gamma-ray burst did affect Earth then, it was not interrupting a half-finished draft. It was cutting into a mature and busy marine world. What would it mean for that world to be aimed at by the universe? Not that the oceans would instantly boil or continents shatter. This is where popular imagination sometimes gets a bit too enthusiastic. The direct effects of a gamma-ray burst at Earth's distance, under plausible scenarios, would not necessarily resemble a cinematic apocalypse visible to every creature at once. The real injury would likely begin in the upper atmosphere. Gamma radiation entering the atmosphere would ionize molecules, particularly nitrogen and oxygen, and this would trigger a chain of chemical reactions. Nitrogen oxides formed in the process can catalytically destroy ozone. Ozone, in turn, is one of Earth's primary shields against harmful ultraviolet B radiation from the sun. Reduce the ozone, and the ordinary daylight that follows becomes much more dangerous. That delayed cruelty is one of the most interesting parts of the story. The burst itself may last seconds or minutes. The damage it initiates in atmospheric chemistry can persist much longer. A short event creates a prolonged vulnerability. It is the sort of mechanism that feels almost bureaucratically unfair. One violent moment in deep space, and then months or years of altered atmospheric conditions on Earth. A brief disturbance at one scale becomes a sustained biological hazard at another, and because the aftermath involves increased ultraviolet radiation from the sun, the source of everyday life becomes part of the extinction pressure. The sky does not merely flash and move on. It remains compromised. Morning light itself becomes more harmful. There is a certain cold elegance in the chain. A distant astrophysical event releases gamma rays. The gamma rays interact with the atmosphere. The atmosphere loses some of its ozone. Ultraviolet radiation increases at the surface and in shallow waters. Organisms exposed to that radiation suffer DNA damage, reproductive stress, and ecological disruption. Food webs begin to wobble. Extinction risk rises. Each step is understandable on its own. Put together, they form a mechanism capable of turning a galactic event into a planetary biological crisis. Nothing in that chain requires malice. Nothing requires coincidence beyond the initial alignment. And yet the overall effect feels almost personally rude. Of course, one should be careful here. The hypothesis is plausible because the physics and chemistry make sense, not because the story is dramatic. Science does not reward a good shiver, it rewards models that fit evidence. So when researchers consider whether a gamma-ray burst might have contributed to the Late Ordovician extinction, they're not asking whether space can be scary. We settled that some time ago. They're asking whether the known effects of a suitably close burst would match the patterns seen in the fossil record, climate proxies, and geochemical data. Could such an event create ozone depletion severe enough to damage marine ecosystems? Would the most affected organisms be those expected to receive the greatest ultraviolet exposure? Could this fit with, or help initiate, the broader environmental upheavals of the Late Ordovician, including glaciation and sea level changes? These are careful questions, and the answers are necessarily probabilistic. Still, even the probability side of the story has its own grim fascination. Gamma-ray bursts are not everyday local hazards, which is fortunate because civilization is already somewhat overbooked with concerns. The galaxy is large, and most bursts happen far enough away to be irrelevant to life on Earth. For a burst to pose a substantial threat, it must occur within a certain distance and point in the right direction. That reduces the risk considerably. Yet over geological timescales, considerably reduced does not mean impossible. Earth has been around for billions of years. Life has had a long time to sit beneath the stars and trust, perhaps unwisely, that distant events will remain distant in their effects. But 1,000,000 years is a long time, and hundreds of millions longer still. Rare events have room to matter when given enough ages in which to occur. That realization has a way of adjusting one's perspective on safety. We often think of survival as a matter of adaptation to local conditions. Can you handle this climate, that predator, this salinity, that competition? Evolution tunes organisms to their environments and rewards robustness where it can. But no trilobite evolves a strategy for a gamma-ray burst. No planktonic larva develops a behavioural response to galactic jet alignment. Some hazards are simply too infrequent, too indirect, too alien to the lived logic of natural selection. Life can adapt beautifully to repeated pressures. It is much less prepared for singular insults from beyond its own system of ordinary threats. That is one reason mass extinctions are so important in the history of life. They are not just periods of elevated mortality. They are moments when the usual terms of survival stop being sufficient. Another unsettling feature of the gamma-ray burst scenario is its invisibility to the victims. We are visual creatures, and even in imagination we tend to expect disaster to announce itself. The sky darkens, the ground shakes, a fire appears on the horizon. But gamma rays are not visible light, and the atmosphere's chemical transformations are not the kind of thing an Ordovician animal would perceive as a single coherent event. The crisis would register biologically, not narratively. Organisms would be damaged, reproduction impaired, populations stressed, ecosystems gradually rearranged. If there were immediate optical effects, they might not mean anything to the creatures living through them. The danger would not arrive as a story. It would arrive as consequences. That makes the whole affair feel oddly clinical. The universe does not roar. It recalculates your atmosphere, and yet there may also have been secondary visual changes, depending on the atmospheric chemistry involved. Nitrogen oxides could alter the colour and transparency of the sky to some extent. Ozone depletion and related reactions might affect climate in ways not immediately obvious. Some models have suggested that nitrogen dioxide produced after such an event could reduce incoming sunlight, potentially contributing to cooling. That is one of the reasons the hypothesis became especially interesting in the context of the end Ordovician, which involved glaciation and major climatic shifts. A gamma-ray burst, in this view, could serve as a trigger or contributing factor, not necessarily the sole explanation for everything that followed, but an initiating insult to atmospheric and ecological stability. It is an attractive possibility because it links astronomy, atmospheric science, climatology, and paleobiology into one chain. Whether it is correct remains debated, but as a scientific idea it is impressively interdisciplinary. Also, it manages to make both skywatchers and fossil specialists equally uneasy, which is a rare diplomatic achievement. It is worth pausing too on the concept of scale in time. The phrase, "the night the universe aimed at Earth," suggests a single evening, a brief episode in darkness. But on an Ordovician Earth, what did night even mean in relation to such a burst? If the burst came while one hemisphere faced away from the sun, then the direct radiation would encounter atmosphere over a darkened world. If it came during day for some regions and night for others, the immediate circumstances would vary geographically. Yet the longer effects on ozone depletion and ultraviolet exposure would unfold globally over time. In that sense, night is more emotional than literal here. It captures the idea of a moment when the sky, so often treated as backdrop, became participant. It marks the turning point at which ordinary planetary life may have fallen under the consequences of a distant catastrophe. And there is something almost intimate in that inversion. We spend so much of our lives thinking of the sky as far away. The stars are decorative until studied. Space is elsewhere. The atmosphere feels local and the cosmos remote. But events like gamma-ray bursts remind us that there is no firm border where one domain stops mattering to the other. Earth lives beneath the galaxy, not apart from it. The atmosphere is not a sealed lid. It is an interface. A planet is both protected by its cosmic setting and exposed to it. Most days that exposure is gentle enough to ignore. Over deep time it can become decisive. None of this means we should become melodramatic every time we look upward. The present-day risk from gamma-ray bursts is very low, and the universe has done us the courtesy of placing no obviously disastrous jet in our immediate direction, as far as current knowledge goes. But the deep past is not obliged to preserve our comfort. It records what can happen, not just what is likely this decade. And in that record, the possibility remains that one of Earth's major biological crises was helped along by an event from the wider galaxy. That possibility, whether or not it proves to be the full story, changes the mood of paleontology in an interesting way. Fossils stop being solely the remains of local ecologies and become, in part, evidence of how planetary life responds to astrophysical disturbance. So as we continue deeper into this ancient world, hold on to that image of alignment, not because it is poetic, but because it is physically central. Somewhere, a star or stellar remnant system ends badly. Energy pours out in a narrow beam. Interstellar space offers very little resistance. Earth rotates on, carrying its seas, its reefs, its drifting plankton, its layered atmosphere, its millions of busy lives. And then, for reasons having nothing to do with merit or preparedness, the line connects. The planet does not know it has been chosen, because it has not been chosen in any moral sense. It has only been included. Sometimes that is enough to rewrite a world, and to understand what kind of world stood there waiting. We need to step more fully into the Ordovician itself, into the seas and creatures that existed before the sky became part of the trouble. Before we can understand what may have been lost, it helps to spend a little time in the world that existed before anything went wrong. Extinction stories have a habit of rushing toward the disaster, as though the only interesting part is the catastrophe itself. But the late Ordovician Earth was not simply a waiting room for ruin. It was a still and remarkably busy planet full of life, motion, chemistry, competition, and quiet routine. If a gamma-ray burst did play some part in what came later, then it did not strike an empty stage. It interrupted a world already deep into its own long and complicated story. The Ordovician period began around 485 million years ago and ended about 444 million years ago. That places it very far back in time, so far that even the familiar landmarks of prehistory vanish. There were no dinosaurs, of course, and not even the earliest giant forests that later transformed the continents. No birds, no mammals, no flowering plants, no grass, no people inventing maps and then drawing the continents in approximately the wrong places before slowly improving. If you stood somehow on a Ordovician shoreline, assuming you had solved the more pressing problem of surviving there in the first place, the world would feel both recognisable and utterly foreign. There would still be oceans, waves, clouds, storms, sunlight, tides, and the turning of day into night. But the land would seem strangely bare, almost unfinished, while the sea would hold most of the real drama. That is one of the first important things to understand about the Ordovician. Life was overwhelmingly marine. The continents existed, certainly, but they were not yet clothed in the rich vegetation that later reshaped the surface of the planet. Land plants were only beginning to edge into existence in very simple forms near the end of the period, and terrestrial ecosystems, in anything like the sense we would recognise, were still mostly absent. If you wanted biodiversity, complexity, and ecological variety, you would head for the water. The Ordovician seas were crowded, active, and in many places astonishingly productive. They were the true centre of life on Earth. The arrangement of the continents was different as well, and as always in geology, that means climate, currents, coastlines, and habitats were different too. Much of the southern hemisphere was dominated by the supercontinent Gondwana, an enormous landmass that included what are now South America, Africa, Antarctica, Australia, and other pieces besides. Laurentia, which would eventually become the core of North America, sat closer to the equator. Baltica and Siberia were separate landmasses as well. The map of Earth, if shown to a modern school child, would likely be met first with confusion, and then with the sort of confidence only children can manage. perhaps a polite suggestion that the teacher had accidentally rotated everything. Yet to the organisms living then, this was simply home. Sea levels during much of the Ordovician were high, and shallow epicontinental seas spread across large parts of the continents. These shallow seas matter enormously because they are among the richest environments for marine life. Sunlight can penetrate them well, nutrients can cycle through them, and their varied bottoms and coastlines create all sorts of habitats. In the Ordovician, these settings became engines of biodiversity. Shelves and shallow basins hosted communities of animals that diversified into a wide array of ecological roles. The sea floor was not a quiet expanse with the occasional lonely shell. It was a thriving patchwork of burrowers, filter feeders, grazers, mobile predators, colonial organisms, and strange forms that seemed to occupy a comfortable position somewhere between familiar and decorative. One of the stars of this world, if star is the right word for an animal famous mainly for having many extinct relatives and a very successful afterlife in museum gift shops, was the trilobite. Trilobites had already been around before the Ordovician, but they remained an important part of marine ecosystems through much of the Paleozoic. They came in extraordinary variety. Some were smooth and streamlined, others heavily ornamented. Some likely burrowed in sediment, others crawled across the seafloor, and still others may have swum more actively. They had segmented bodies, compound eyes in many cases, and the enviable if somewhat desperate ability to roll up for protection. To modern eyes they can look like little armoured biscuits with ambitions, but in their time they were a major and widespread group. They were not alone. Brachiopods were abundant, and these are creatures often mistaken for clams by people who have not yet had the experience of being lovingly corrected by a paleontologist. Brachiopods have two shells, yes, but they are built differently from bivalves and belong to a separate lineage. In the Ordovician they flourished in vast numbers, attached to the sea floor or resting upon it, filtering food from the water. Bryozoans formed colonial structures, delicate little cities of interconnected individuals. Crinoids, relatives of starfish and sea urchins, waved feathery arms into currents to capture food, rooted in place by stems that gave them a plant-like appearance despite their animal nature. Corals and coral-like organisms contributed to reef systems. Graptolites drifted in the water column and would later become especially useful to geologists because their rapid evolution and wide distribution make them excellent index fossils. Cephalopods, including straight-shelled nautiloid forms, moved as predators through the seas with all the quiet authority of creatures that had worked out the advantages of tentacles and mobility. It is easy when listing ancient organisms to make the world sound like a cabinet of curiosities. This too can be charming, but it misses the ecological point. These were not isolated oddities floating around waiting to be labelled. They were parts of functioning ecosystems. Energy flowed through these communities. Predators hunted prey. Filter feeders processed suspended particles. Burrowers reworked sediment. Larvae drifted, settled, and matured. Colonial organisms expanded across available surfaces. Competition shaped where things lived and how they fed. The Ordovician seas were not merely inhabited, they were organised. In fact, the Ordovician is famous for one of the great diversification events in the history of animal life, often called the Great Ordovician Biodiversification Event. After the earlier Cambrian explosion had established many major animal body plans, the Ordovician saw a dramatic increase in the diversity and ecological complexity of marine organisms. This was not just more species in some simple numerical sense. It was a deepening of ecosystems. Communities became more layered. Different feeding strategies expanded. New relationships formed between organisms and environments. Marine food webs became richer and in many ways more modern in structure. If the Cambrian was a kind of exuberant opening act in animal evolution, the Ordovician was a period in which many groups settled into more elaborate and enduring ecological roles. Why this diversification happened is still discussed, and as with many broad evolutionary events, there is no single tidy answer. changes in sea level, climate, oxygenation, nutrient availability, tectonics, and ecological interactions all likely played roles. More habitats became available as shallow seas spread. Continental movement altered ocean circulation. Cooling trends in some intervals may have helped create conditions favourable for diversification. Once ecosystems become more complex, they can also generate their own opportunities, with one innovation creating new niches for another. Evolution, after all, is a bit like renovating a house while continuing to live in it. Add one staircase, and suddenly someone invents upstairs arguments. New structures create new possibilities. The water itself would not have looked exactly as modern seawater environments do. Ocean chemistry has changed over geological time, and the Ordovician oceans existed under atmospheric conditions not identical to today's. Oxygen levels, carbon dioxide concentrations, nutrient cycles, and biological productivity all interacted differently than they do now. Even so, the basic truth remains familiar enough. The seas were the place where most of the living action happened. Reefs and hard grounds hosted attached communities. Softer seafloors held burrowers and crawlers. Open waters contained drifting life and active swimmers. Sunlit shallow zones were especially important, because this is where much primary productivity and ecological richness concentrated. And that detail will matter later, because environments most full of life can also become the most exposed when sunlight itself becomes part of the problem. The continents, by contrast, were quiet, in a way that would seem uncanny to us. There were probably microbial mats in places, perhaps some early simple plants edging onto damp ground by the later Ordovician, and fungi likely present in some form, but there were no forests murmuring in the wind, no insects humming, no vertebrates padding along riverbanks. The silence of Ordovician land would have been immense. Rock, sediment, bare surfaces, perhaps weathered by rain and streams, perhaps edged with primitive biological films, but nothing like the densely occupied terrestrial world we know today. If you wanted spectacle, you went to the shore and looked outward, not inland. Climate through the Ordovician was not static. For much of the period, conditions were generally warm, and high sea levels reflected that relatively greenhouse-like world. But toward the end of the period, major climatic changes took place, including glaciation associated with Gondwana moving over the South Pole. Ice sheets expanded, sea levels fell, and marine habitats contracted or changed drastically. These shifts are central to the traditional explanation for the end Ordovician extinction. Yet before those later disruptions sharpened, there existed long spans of time in which the seas supported a broad flourishing of life. It is easy, knowing the extinction is coming, to see the Ordovician as doomed. But that is hindsight talking. For the organisms living through its earlier and middle stretches, this was not a world in decline. It was a world in expansion. There is something almost tender in that realization. Ancient life does not know it is ancient. It does not know it will later be called foundational, transitional, or vulnerable. A brachiopod filters food because that is what it does. A trilobite crawls across sediment because that is where it lives. Graptolites drift. Crinoids feed. Entire populations rise and fall according to local conditions, competition, and chance. Evolution unfolds with no sense of a coming headline. The Ordovician biosphere was simply busy being itself, full of small routines repeated across millions of years. In that sense, every past world is innocent. Not morally innocent, of course. Predators were perfectly happy to eat whatever was available, but innocent of narrative. It does not know what is about to happen next. One especially important feature of this world, given where our story is going, is the role of shallow marine environments. Many Ordovician organisms lived in waters where sunlight still penetrated easily, where plankton productivity supported food webs, and where the interaction between atmosphere, climate, and ocean chemistry was especially immediate. This made such habitats wonderfully productive, but also potentially sensitive. If conditions change quickly, these ecosystems could be hit hard. A drop in sea level could strip away vast areas of shallow shelf habitat. Changes in temperature could rearrange circulation and oxygen levels. Increased ultraviolet radiation, if ozone were depleted, could damage organisms living in or near the upper water column and affect larval stages especially vulnerable to environmental stress. Richness and exposure often live side by side. It is worth picturing these seas not as uniformly crowded but as varied landscapes in their own right. There were muddy bottoms and carbonate platforms, reefs and quieter basins, regions with different salinities, currents, and sediment inputs. Some communities were dominated by attached suspension feeders, others by mobile benthic organisms, others by planktonic forms in the water column above. Storms could disturb sediments. Seasonal changes, though not identical to modern ones everywhere, would still have shaped biological rhythms. Reproduction, settlement, feeding and predation all followed patterns built from local and global conditions. The Ordovician Ocean was not one habitat. It was a network of many, and as in any living network, resilience had limits. Diversity can provide stability, but it also creates interdependence. When many species occupy specialized roles, disturbance can ripple in unexpected ways. Remove one habitat and another suffers. Damage primary production, and filter feeders and grazers feel it. Stress larvae in surface waters, and future adult populations decline later. Shift climate and currents, and the geographical ranges of species begin to compress, expand or break apart. Extinctions are often less like a single blow and more like a series of tightened constraints. The Ordovician world, for all its abundance, was still a system made of biological parts that depended on one another and on relatively stable environmental conditions. The fossil record gives us glimpses of this richness, though always in partial form. Hard parts preserve better than soft tissue, which means our picture is inevitably biased towards shells, skeletons, tubes, and structures more likely to survive burial and lithification. A soft-bodied organism that once played some modest but meaningful role in Ordovician ecology might leave almost no trace, while a heavily calcified shell has an excellent chance of joining the geological conversation. Even so, the surviving record is rich enough to show clear patterns of diversification, distribution, and eventual loss. Whole assemblages can be reconstructed. Community changes can be tracked through time. Extinction intensity can be measured across groups and environments. Fossils, when numerous enough, become more than beautiful remains. They become statistical whispers from lost worlds, and what they whisper about the Ordovician before the extinction is not fragility alone, but success. This was a planet in which marine life had found many ways to flourish. Ocean ecosystems were maturing into more intricate forms. Lineages expanded geographically. Community structures became more elaborate. There is a temptation, when telling stories of ancient disaster, to treat everything before the event as mere setup. But in the Ordovician, the setup lasted tens of millions of years. It was a substantial age in its own right, not simply a prelude to loss. Perhaps that is why the later crisis feels so severe. Mass extinctions are always sad in the abstract, but they become more meaningful when one has some sense of what was there to be lost. Not just species names in a chart, but ways of living, ecological roles, communities, and evolutionary possibilities. The end Ordovician extinction did not merely reduce a number, it cut into one of the great flourishing marine worlds of Earth history. It disrupted a biosphere that had become broad, active, and richly structured across shallow seas and continental shelves. The sky above that world for most of its living inhabitants would have seemed ordinary enough. Sunlight by day, darkness by night, weather as weather. No cosmic menace written visibly across the horizon. The atmosphere did its patient work. Ozone filtered ultraviolet radiation. The sun drove climate and productivity without becoming an excessive biological weapon. Organisms near the surface lived within those limits because those limits had been stable enough to trust. That trust, if we may call it that, is one of the quiet conditions under which life prospers. Not safety in any absolute sense, but relative predictability. The world need not be gentle. It only needs to be consistent enough for adaptation to make sense. So this was the Earth before the flash, before any putative burst from deep space had a chance to interfere, before atmospheric chemistry may have shifted toward danger, before glaciation and sea level fall pushed already vulnerable ecosystems harder still. A marine planet, productive and varied, with continents arranged unlike our own, shorelines spreading into shallow seas, animals diversifying in numbers and forms, and the land still largely waiting for its later green transformation. It was not our world, but it was a fully realized one, and to understand how something from deep space could threaten it, we now need to leave the shoreline for a while and look outward, toward the phenomenon itself, toward the violent astrophysical event whose brief brilliance may have reached across the galaxy and changed the terms of life below. If you ask what a gamma-ray burst is, the simplest answer is that it is an extremely powerful release of energy in the form of gamma radiation, lasting anywhere from a fraction of a second to several minutes. That sounds straightforward enough, but like many simple definitions, it hides more than it reveals. To really understand what we're dealing with, it helps to slow down and unpack the pieces, because this is one of those phenomena where the scale is so far outside everyday experience that the mind tends to either exaggerate it into something cinematic or shrink it into something manageable. In truth, it is neither of those things. It is something that sits quietly in the category of real, observed, and deeply inconvenient if you happen to be in the wrong place. Gamma rays themselves are not mysterious in the sense of being a separate substance. They are part of the electromagnetic spectrum, which is the same family that includes radio waves, microwaves, infrared radiation, visible light, ultraviolet radiation, X-rays, and finally gamma rays at the most energetic end. The difference between these forms of radiation is not what they are made of, but how much energy they carry. Visible light is what your eyes are tuned to detect. Gamma rays, by contrast, carry far more energy per photon, and that additional energy gives them their reputation. When gamma rays interact with matter, they can penetrate deeply, ionize atoms, and break molecular bonds in ways that are biologically disruptive. Under normal circumstances, this is not something that demands your attention. The atmosphere absorbs most high-energy radiation before it reaches the surface, and whatever small amounts do get through are part of a background that life has long adapted to. The problem arises when the quantity and intensity increase dramatically. A gamma-ray burst is not a gentle trickle of radiation. It is a sudden, concentrated surge, often arriving in a tightly focused beam rather than spreading evenly in all directions. For a brief period, it can release as much energy as the sun will produce over billions of years. That is not a poetic exaggeration. It is the sort of number that requires you to pause and consider whether the sentence has made a mistake. It has not. The universe occasionally behaves in ways that make our ordinary comparisons look very small. These bursts were first discovered not by astronomers searching for them, but by satellites built for an entirely different purpose. During the Cold War, the United States launched a series of satellites designed to detect gamma radiation from nuclear tests. The idea was to monitor compliance with treaties by watching for suspicious bursts of high-energy radiation in Earth's vicinity. Instead, the satellites began detecting gamma-ray flashes coming from deep space. They did not match the signature of nuclear explosions on Earth, and they appeared to originate from random directions across the sky. For a time, they were simply puzzling events, recorded and catalogued without a clear explanation. It took years of observation and improved instrumentation to understand that these bursts were not local at all, but cosmological, coming from immense distances. Once that became clear, the scale of the phenomenon expanded dramatically. If you detect a certain amount of energy at your instruments, and the source is very far away, then the actual energy released at the source must be enormous. Gamma-ray bursts went from being odd signals to being some of the most energetic events known in the universe. That shift in understanding is one of those quiet scientific moments that changes everything without much outward drama. A set of mysterious blips becomes a window into catastrophic stellar processes happening across the cosmos. As observations improved, scientists began to notice that gamma-ray bursts were not all identical. They could be grouped broadly into two main categories based on their duration. Long-duration bursts, which last more than about 2 seconds, and short-duration bursts, which last less than that. This division might sound arbitrary, but it turns out to reflect different underlying physical processes. Long-duration gamma-ray bursts are generally associated with the collapse of massive stars. Imagine a star much larger than our Sun reaching the end of its life. It has spent millions of years fusing lighter elements into heavier ones, building up an internal structure that eventually becomes unstable. When nuclear fusion can no longer support the star against gravity, the core collapses. In some cases, this collapse leads to the formation of a black hole. As material falls inward, it does not simply disappear quietly. It forms an accretion disk around the newly formed black hole, heating up and releasing enormous amounts of energy. Under certain conditions, this system produces jets of material and radiation that shoot out along the rotational axis of the collapsing star at nearly the speed of light. These jets can punch through the outer layers of the star and escape into space, carrying with them intense beams of gamma radiation. If one of those jets happens to be pointed toward Earth, we observe it as a long-duration gamma-ray burst. If it is pointed elsewhere, we see nothing at all. The event still happens, but it is effectively invisible to us. This directional nature is crucial. It means that the danger of a gamma-ray burst is not uniform. It depends on alignment. The universe does not need to aim in a conscious sense, but geometry alone can produce outcomes that feel very personal from the perspective of a planet caught in the beam. Short-duration gamma-ray bursts, on the other hand, are thought to arise primarily from the merger of compact objects, such as neutron stars. A neutron star is what remains after a massive star has exploded in a supernova, leaving behind a core so dense that protons and electrons have been crushed together into neutrons. These objects are incredibly compact and massive, and when two of them orbit each other in a binary system, they gradually spiral inward due to the emission of gravitational waves. Eventually they collide in a violent merger that releases a tremendous amount of energy, including a burst of gamma radiation. These mergers are not just important for gamma-ray bursts. They are also sites where heavy elements are forged, including gold, platinum, and other materials that later become part of planets, and eventually jewellery. It is one of those mildly disorienting facts that something as delicate as a ring can trace its origins back to an event violent enough to shake space-time itself. The universe is not particularly concerned with keeping its processes neatly categorized into gentle and destructive. It tends to mix those qualities together in ways that are both productive and alarming. In both types of gamma-ray bursts, the key features are the intensity of the radiation and the narrowness of the emission. The energy is not spread evenly in all directions. It is concentrated into jets, which makes the observed brightness much higher if you're inside the beam. This is why gamma-ray bursts can appear so bright even when they are billions of light-years away. It is also why they can be dangerous at much greater distances than one might initially expect. A diffuse source would need to be very close to have a significant effect. A focused beam can carry damaging energy across much larger spans of space. Now, it is important to keep perspective here. The galaxy is vast, and gamma-ray bursts are relatively rare events in any given region. The chances of a burst occurring close enough and aligned in just the right way to affect Earth are low on human timescales. This is not something that is expected to happen next week, or even next million years. But when we stretch our view across hundreds of millions of years, the probability becomes less negligible. Geological time provides many opportunities for rare events to occur. The Ordovician period itself lasted tens of millions of years, and the broader history of life spans billions. Over such durations, even low probability events can become part of the story. What would it look like, from Earth's perspective, if a gamma-ray burst were directed toward the planet? Interestingly, it would not necessarily be visually spectacular in the way we might expect. Gamma rays are not visible to the human eye, and most of the incoming radiation would interact with the upper atmosphere. There might be secondary effects such as changes in atmospheric chemistry that could influence the colour or transparency of the sky, but there would be no obvious fireball streaking across the horizon. The real action would be taking place at altitudes where the air is thin and where chemical reactions can propagate through the atmosphere in ways that matter for ozone. This is where the connection to planetary vulnerability becomes more concrete. When gamma rays enter the atmosphere, they can break apart nitrogen molecules and lead to the formation of nitrogen oxides. These compounds play a key role in ozone depletion because they catalyse reactions that convert ozone into ordinary oxygen. The ozone layer, which sits high in the atmosphere, is particularly important because it absorbs a large portion of the sun's ultraviolet B radiation. If ozone is reduced significantly, more of that ultraviolet radiation reaches the surface and shallow waters, where it can damage living tissue. The damage from increased ultraviolet radiation is not always immediate in a dramatic sense. It affects DNA, interferes with cell division, and can reduce reproductive success. In marine environments, plankton near the surface can be particularly vulnerable, and since plankton form the base of many food webs, their decline can ripple through entire ecosystems. Larval stages of many organisms, which often drift in the upper layers of the ocean, are also sensitive to environmental stress. If enough of these early life stages fail, populations can decline even if adult organisms seem unaffected at first. This is one of the reasons the gamma-ray burst hypothesis for the end Ordovician extinction focuses not on a single moment of destruction, but on a cascade of effects. The burst itself is brief. The atmospheric changes it triggers can last much longer. The biological consequences unfold over extended periods, interacting with other environmental stresses such as climate change and sea level fluctuations. It is not a simple cause and effect story with a single visible trigger. It is a chain of processes that begins with high-energy physics and ends with ecological collapse. There is also the question of how far away a gamma-ray burst would need to be to have a significant effect on Earth. Estimates vary depending on the assumptions used in the models, but a commonly discussed range is within a few thousand light-years. That might sound like a comfortable distance, but in galactic terms it is relatively close. The Milky Way is about 100,000 light-years across. A sphere with a radius of a few thousand light-years around Earth still contains a substantial number of stars. Over long periods of time, it is not unreasonable that events within that volume could occur. At the same time, not every gamma-ray burst within that distance would necessarily be dangerous. The orientation of the jet is critical. If the beam is not directed toward Earth, the impact is minimal. This reduces the risk significantly. It also makes the hypothesis harder to test, because we cannot simply count nearby bursts and assume they would have affected us. We need to consider both distance and direction, as well as the specific characteristics of each event. Another factor is the duration and intensity of the burst. Short bursts and long bursts differ not only in their origin, but also in how they deliver energy. The total energy, the time profile, and the interaction with the atmosphere all matter for the resulting chemical changes. Modelling these effects requires combining astrophysics with atmospheric chemistry and climate science, which is part of what makes this topic both challenging and interesting. It sits at the intersection of multiple fields, each with its own uncertainties and methods. One might wonder whether there is any direct evidence of a gamma-ray burst affecting Earth in the past. This is where things become more subtle. Unlike an asteroid impact, which can leave a crater and a layer of debris rich in extraterrestrial material, a gamma-ray burst does not leave a clear, localized physical marker. Its effects are mediated through the atmosphere and then through biological systems. This means that any evidence must be indirect, inferred from patterns in the fossil record, geochemical signatures, and models of atmospheric change. For the End Ordovician extinction, researchers have looked at the distribution of extinctions across different environments and organisms. Some patterns, such as the vulnerability of surface-dwelling and shallow water organisms, are consistent with increased ultraviolet radiation. There are also isotopic and sedimentary records that reflect climate changes and glaciation. The challenge is to determine whether these patterns require an additional trigger, like a gamma-ray burst, or whether they can be explained entirely by more traditional factors such as tectonics and climate alone. This is why the gamma-ray burst idea remains a hypothesis rather than a confirmed cause. It is plausible, it fits certain aspects of the data, and it provides a mechanism for rapid atmospheric change without leaving obvious impact evidence. But it competes with other explanations that are also supported by data. Science does not choose the most dramatic story. It weighs the evidence and looks for the explanation that best accounts for all observations. Still, even as a possibility, gamma-ray bursts expand our understanding of what kinds of events can influence life on Earth. They remind us that the planet is not isolated. It exists within a galaxy where processes of immense scale and energy occur regularly, even if they are usually far away. Most of the time, those processes have no noticeable effect on us, but occasionally, under the right conditions, they might. And that brings us back to the Ordovician world, still busy in its shallow seas, still expanding in diversity, still unaware of any threat beyond the ordinary rhythms of its environment. Above it, the atmosphere continued its quiet work, filtering radiation, maintaining conditions that life had come to rely on. Far beyond that, somewhere in the galaxy, stars lived out their lives, some of them approaching violent ends that would release energy on a scale difficult to fully grasp. Whether one of those events aligned with Earth at just the wrong moment is a question we are still exploring. But to understand what would happen next if it did, we need to look more closely at how such a burst could interact with our planet, how something so distant could reach into the chemistry of the sky and begin a chain of changes that life below could not easily escape. The strange thing about a cosmic event affecting Earth is that it does not need to cross space in the way our instincts expect. We are very comfortable with the logic of objects. A meteor can hit you because it travels from there to here. A storm reaches you because winds and clouds move into your region. Even sunlight, for all its familiarity, feels acceptable because it arrives steadily and has done so every day of our lives. But a gamma-ray burst belongs to a different category of threat. It does not need to creep closer over centuries or crash into the ground in dramatic fashion. It only needs to happen, point the right way, and send energy across the vacuum. If the alignment works out badly for us, the atmosphere takes the first blow, and from there the consequences begin to unfold in ways that are slower, quieter, and more complicated than a simple impact. That is the key to understanding how a burst across the cosmos could strike our planet. It is not really the planet's surface that gets struck first. It is the air above it. That air, which feels so ordinary when we breathe it or complain about it being too cold or too damp, is one of the most important protective systems life has ever had. We speak about the atmosphere casually because we live inside it all the time, but it is an extraordinarily sophisticated filter. It shields the surface from harmful radiation, moderates temperature, participates in chemistry essential to climate and life, and creates a buffer between the raw conditions of space and the delicate needs of biology. Most days it performs these tasks without applause, which is typical of the most essential employees. If a gamma-ray burst were directed toward Earth from a close enough distance, the first stage of the crisis would begin high in that protective layer. The incoming gamma rays would reach the upper atmosphere and interact with its molecules, especially nitrogen and oxygen. Gamma rays carry enough energy to ionize atoms and break apart stable molecular bonds. This means they can take the familiar ingredients of the atmosphere and, through brute energetic interference, turn them into chemically reactive fragments. In other words, they do not merely pass through like indifferent tourists. They arrive, cause trouble, and leave the chemistry considerably less settled than they found it. Nitrogen is especially important in this story because Earth's atmosphere is mostly made of it. In normal conditions, nitrogen gas exists as pairs of atoms tightly bound together in molecules that are fairly stable. That stability is useful. It keeps nitrogen from constantly reacting with everything in sight. But when a large burst of high-energy radiation arrives, those bonds can be broken. Free nitrogen atoms and ionized forms then react with oxygen, producing a family of compounds known as nitrogen oxides. These are not exotic substances in the broad sense. We deal with nitrogen oxides in modern pollution and atmospheric science all the time. The problem is what they do when they accumulate in the upper atmosphere. They catalyze reactions that destroy ozone. Ozone, despite being just a form of oxygen made of 3 oxygen atoms instead of the usual 2, has an outsized importance in the history of life. It forms a layer in the stratosphere that absorbs much of the sun's ultraviolet B radiation, the part of the solar spectrum especially capable of damaging biological molecules. Ozone is not a thick shield in any muscular sense. It is more like a thin but highly effective chemical veil. Life on land and in shallow water depends on it far more than most organisms realise, which is probably just as well, because worrying about atmospheric trace gases is not a productive use of a trilobite's afternoon. Once nitrogen oxides begin to build up after a gamma-ray burst, they can destroy ozone through catalytic cycles. That word catalytic matters because it means the nitrogen oxides are not consumed in one simple reaction and then gone. They can keep participating in ozone destruction repeatedly. A relatively modest amount of reactive compounds can therefore produce a very large loss of ozone over time. This is one reason the aftermath of a gamma-ray burst can extend far beyond the few seconds or minutes of the burst itself. The energy input is brief, but the atmospheric consequences can linger for months or years, depending on the details of circulation, chemistry, and recovery. That delayed damage is one of the more unnerving features of the whole scenario. If an asteroid hits, there is at least the decency of immediate clarity. It has happened. The crater is there. Dust rises. Everyone agrees something has gone rather badly. A gamma-ray burst, by contrast, can deliver its first insult invisibly and leave the atmosphere to carry on the harm afterward. The planet may appear outwardly intact. There is no crater, no mountain-sized object lodged somewhere inconvenient. Instead, the filter in the sky becomes less effective, and then ordinary sunlight starts doing extraordinary damage. This is where the event ceases to be purely astrophysical and becomes ecological. The sun, under normal circumstances, is not an enemy. It is the foundational energy source for almost every ecosystem on Earth. It warms the planet, drives weather, powers photosynthesis, and sets the rhythms of day and season. But the friendliness of sunlight depends on the atmosphere adjusting what reaches the surface. Remove enough ozone, and the sun becomes a harsher companion. Ultraviolet B radiation increases at the surface and in the upper layers of the ocean. That radiation is particularly harmful to DNA and other cellular components. It can impair photosynthesis, damage tissues, reduce reproductive success, and interfere with development in many organisms. If we shift our attention back to the Ordovician world, this matters enormously. Most life at that time lived in the seas, and a great deal of it lived in shallow, sunlit marine environments. Those environments were productive precisely because they existed where light could penetrate. Photosynthetic organisms in surface waters, larvae drifting near the top of the water column, filter-feeding communities in clear shallows, all of these benefited from the availability of sunlight under ordinary conditions. But that same dependence becomes a vulnerability when ultraviolet radiation intensifies. The upper ocean is not a uniform refuge, it is where exposure is greatest. A gamma-ray burst therefore does not need to strike fish or trilobites directly with some cosmic beam in a crude sense. It changes the terms of exposure. It alters the atmospheric shield, and then the ecosystems most dependent on near-surface conditions begin to suffer. Primary productivity may decline if phytoplankton are damaged. Reproductive stages may fail if eggs and larvae are especially sensitive to ultraviolet stress. Organisms adapted to clear, shallow waters may lose the very environmental stability that made those habitats so rich. That can ripple outward into food webs, because marine ecosystems are built on layered dependencies, harm the base, and the effects move upward. Harm the young and adult populations decline later. Harm several parts at once, and systems begin to unravel. There may also be climate consequences, which adds another twist to the mechanism. Some atmospheric models suggest that the nitrogen dioxide produced after a large radiation event could absorb visible light and reduce the amount of solar energy reaching the lower atmosphere and surface. That means the same chemistry responsible for ozone destruction could also contribute to cooling. This is one of the reasons the gamma-ray burst hypothesis became especially interesting in discussions of the end Ordovician extinction. The Late Ordovician involved glaciation and significant climatic change. If a burst helped initiate atmospheric alterations that both depleted ozone and reduced incoming sunlight, then it could, in principle, serve as a trigger or contributing factor to broader environmental disruption. Notice how layered this becomes. First comes the burst. Then the upper atmosphere absorbs the energy and reacts chemically. Ozone declines. Nitrogen compounds build up. Ultraviolet radiation increases. Potential cooling follows through altered atmospheric opacity. Ecosystems suffer from more than one side at once. This is not a single neat arrow from cause to effect. It is a web of interacting consequences. That complexity is part of why scientists model such scenarios carefully, rather than treating them as one dramatic switch being flipped. The atmosphere is a system, and when you disturb one part of it, other parts respond. Chemistry affects radiation balance. Radiation balance affects climate. Climate affects ice formation, sea level, and circulation. Biology depends on all of those. A useful way to think about it is to imagine the atmosphere as a layered agreement between space and life. Most of the time, the agreement holds. High-energy radiation is intercepted. The sun's output is moderated. Surface conditions remain within limits that organisms can adapt to. A gamma-ray burst does not destroy the agreement outright, but it tears up enough clauses that life suddenly faces new conditions it was not built to handle. The danger is not simply space radiation reached Earth. It is Earth's atmospheric contract with the sun was rewritten without consultation. Another question naturally arises here. Would the whole planet be affected equally? The answer is probably not in detail, though the broad atmospheric consequences could be global. The side of Earth facing the burst would receive the initial radiation input, and atmospheric reactions might begin more intensely there. But circulation in the atmosphere would spread reactive compounds over time. Ozone depletion would not remain neatly local forever. Different regions might experience different degrees of impact depending on latitude, season, atmospheric dynamics, and the duration of the aftermath. But the problem would not politely stay where it started. Once the chemistry of the upper atmosphere is altered significantly, planetary systems begin sharing the inconvenience. Latitude may matter in other ways too. Ozone chemistry varies by region, and the biological consequences of increased ultraviolet radiation depend partly on how much solar exposure an area receives. Equatorial and subtropical regions, already receiving strong sunlight, might become especially difficult environments under severe ozone depletion. At the same time, if climatic cooling and glaciation are amplified, polar and subpolar regions experience their own transformations. The end result is not one universal experience, but a patchwork of stresses, some immediate, some delayed, some more chemical, others more climatic. Extinctions rarely arrive with elegant simplicity. Distance also matters, of course, and not every gamma-ray burst in the galaxy would be a threat. For a burst to produce the kind of atmospheric damage under discussion, it likely needs to occur within a few thousand light years and be pointed toward Earth. In everyday language, A few thousand light years sounds safely remote, and it is remote by any human standard. We struggle enough with commutes measured in minutes, but in galactic terms it is close enough for high-energy radiation, if narrowly focused, to remain significant. The Milky Way is a large place, but not so large that no dangerous events can ever happen within that radius over hundreds of millions of years. Still, the beam orientation requirement is a major filter on risk. Many gamma-ray bursts happen without affecting us because their jets point elsewhere. This is an important reason why Earth has not been repeatedly sterilised by cosmic tantrums every few geological weekends. The universe is dangerous, yes, but it is also full of directions. To be harmed, you need a burst that is both near enough and aligned badly enough. That reduces the frequency substantially. It also means that if such an event did affect Earth in the Ordovician, it would have been a matter of chance alignment rather than the inevitable consequence of living in a galaxy. Chance alignment, however, is still perfectly capable of ruining a biosphere. One of the more elegant but frustrating parts of this hypothesis is that the mechanism can operate without leaving an obvious geological smoking gun. A large impact leaves shocked minerals, impact spherules, iridium anomalies, and, if one is very lucky, a crater. Flood basalts leave lava and geochemical traces. A gamma-ray burst leaves no chunk of itself behind. It leaves altered chemistry and biological stress patterns. This makes it harder to test, but not impossible. Scientists look for extinction selectivity, environmental patterns, isotopic records, and climate signals that match what would be expected from a burst-induced atmospheric crisis. For example, if enhanced ultraviolet radiation played a major role, one might expect organisms living in surface waters or shallow marine settings to be hit particularly hard compared with those in deeper, more sheltered environments. If climate cooling followed, there should be evidence compatible with that as well. The challenge is that the Late Ordovician already has strong conventional explanations involving glaciation, sea level fall, habitat loss, and oceanographic changes. Those mechanisms are real and important. The gamma-ray burst hypothesis does not necessarily need to replace them entirely to be interesting. It could function as a trigger that sets some of them in motion, or as an added stress layered onto a system already vulnerable to climatic shifts. In Earth history, causes are often not solitary. A biosphere can absorb one blow and still recover. 2 or 3 interconnected pressures arriving in sequence are far harder to manage. There is another subtle aspect worth mentioning. Ozone depletion is not merely a matter of letting in more ultraviolet radiation for a few afternoons and then moving on. Biological systems respond in complicated ways to sustained increases in ultraviolet exposure. Photosynthetic organisms can be damaged directly. DNA repair mechanisms can be overwhelmed if the stress is severe enough. Developmental stages may be especially vulnerable. Mutation rates may rise. Some organisms can retreat to deeper waters or shaded environments, but many cannot do so effectively, especially if their life cycles require time near the surface. Ecological consequences often lag behind the initial physical insult. Populations may continue for a while on momentum, only to decline later when reproduction fails or food sources diminish. This makes the pattern of extinction more drawn out than a single theatrical catastrophe, which again fits the idea of a burst acting through atmospheric mediation rather than through immediate physical destruction. And then there is the quiet cruelty of sunlight becoming the delivery system for ongoing damage. After the burst is gone, the sun continues rising as usual. There is no reason, from the perspective of an Ordovician organism, to associate the morning light with a distant stellar collapse that happened perhaps thousands of light years away. Yet that is the point. The cosmos does not need to remain present to keep harming you once it has altered your atmosphere. It simply adjusts the settings and lets local conditions do the rest. If all this sounds a bit unfair, that is because it is. The Earth's biosphere is resilient in many ways, but resilience does not imply preparedness for every kind of insult. Evolution can shape tolerance to predictable ranges of sunlight, temperature, chemistry, and predation. It cannot reasonably plan for a burst of gamma radiation from a dying star in another part of the galaxy. There is no adaptive strategy for hope the beam points elsewhere. That is not a trait. It is a prayer dressed as geometry. So when we ask how a burst across the cosmos could strike our planet, the answer is not by arriving as a flaming object or a visible monster in the sky. It strikes by reaching the atmosphere first, by turning stable molecules into reactive ones, by depleting ozone, by increasing ultraviolet stress, by potentially reducing sunlight in other wavelengths enough to affect climate, and by allowing those atmospheric changes to cascade through marine ecosystems already dependent on narrow environmental balances. It is a planetary injury delivered through chemistry. The event happens in space, but the damage unfolds in air, water, and living tissue. That is why the next step in our journey has to remain with the atmosphere for a while longer. We need to look more closely at what happens when ozone begins to fail, because this is the point where the abstract cosmic threat becomes an earthly biological crisis, where high-energy photons from deep space are translated into something life can feel in every cell exposed to the changed light above. For most of Earth's history, the ozone layer has done its work so quietly that life rarely had any reason to notice it. It sat high above the weather, high above the ordinary business of waves and clouds and living things, intercepting much of the sun's ultraviolet B radiation, before that radiation could do widespread biological harm. Ozone is not a thick wall or some dramatic glowing shield stretched over the planet. It is a relatively thin concentration of molecules in the stratosphere, fragile in one sense and absolutely essential in another. Its importance lies not in bulk but in function. It filters, it moderates, it keeps the sunlight that reaches the surface within a range that biology can handle. And if a gamma ray burst struck Earth during the Ordovician, the first truly planetary sign of trouble may have been the moment that quiet filtering system began to fail. That failure would not have looked like a hole suddenly tearing open in the sky. It would not have been visible in the clean theatrical way disasters often are in fiction. No Ordovician creature would have gazed upward and thought, with perfect scientific clarity, that stratospheric chemistry had entered a dangerous new phase. The crisis would begin above notice, in thin air and molecular reactions. High-energy gamma radiation from the burst would enter the atmosphere and ionize it, breaking apart stable nitrogen and oxygen molecules. Once those molecules were split into reactive fragments, the chemistry of the upper atmosphere would shift rapidly. Nitrogen oxides would form in abundance, and those compounds are particularly troublesome because they catalyze the destruction of ozone, rather than simply reacting once and disappearing. A brief burst of radiation could therefore trigger a much longer period of ozone depletion. That is one of the most unnerving parts of the scenario. The burst itself might last only seconds or minutes. The atmospheric injury it initiates could persist for years. Thomas and colleagues modelled the effects of a galactic gamma-ray burst and found that a burst within a few kiloparsecs could quickly remove much of Earth's protective ozone, allowing a substantial increase in solar UVB at the surface. Mellott and colleagues likewise argued that such an event could plausibly initiate the Late Ordovician extinction by producing severe ozone loss and subsequent biological stress. In other words, the violence of the cosmic event is short, but the vulnerability it creates can linger. The sky does not need to remain actively under assault. It only needs to be chemically altered badly enough that ordinary sunlight becomes a sustained hazard. To appreciate how serious that is, it helps to remember what ozone actually does. Ozone forms when ultraviolet radiation from the sun splits ordinary oxygen molecules, and the resulting oxygen atoms combine with other oxygen molecules. The stratosphere constantly creates and destroys ozone in a dynamic balance, and that balance determines how much ultraviolet radiation is absorbed before reaching lower altitudes. When nitrogen oxides are injected into the system in large amounts, they interfere with that balance by helping convert ozone back into ordinary oxygen again and again. This is not a one-time loss. It is a chemically efficient unravelling. A modest amount of catalytic trouble can punch far above its weight, rather like one person in a quiet office who has decided that every printer must jam today. The timing of the failure, if one could call it a day at all, would likely be less a single instant than the start of a chain. The radiation arrives, the atmosphere ionizes, nitrogen oxides accumulate, ozone begins to decline, atmospheric circulation then spreads the chemical products through wider regions. The initial interaction might be strongest on the side of Earth facing the burst, but the longer atmospheric consequences would not remain neatly local. Over time, circulation would transport reactive compounds around the globe, turning what began as a directional insult into a planetary atmospheric problem. There would be regional variation certainly, and latitude would matter, but the larger story would be global. Once the chemistry of the stratosphere is pushed far enough off its normal track, the whole biosphere begins negotiating with a different sky. During the Ordovician, that mattered especially because life was concentrated in the seas, and many of the richest ecosystems occupied shallow sunlit marine environments. These settings were productive precisely because they received enough light to support photosynthesis and sustain layered food webs. But they were also the habitats most exposed to increased ultraviolet radiation once ozone protection weakened. Organisms living near the surface of the ocean, plankton drifting in the upper water column, larvae and eggs of marine animals, and communities built around clear shallow shelves would all be placed in the path of stronger UVB. The danger would not arrive as a monstrous wave. It would arrive as morning light that had become harsher than it used to be. Modern biology gives us a clear sense of why that matters. Increased ultraviolet B radiation damages DNA, disrupts cell division, impairs photosynthesis, and can reduce survival and reproduction in a wide variety of organisms. In marine systems, phytoplankton and other photosynthetic microorganisms are especially important because they sit near the base of food webs. If they are suppressed, the effects can ripple outward through filter feeders, grazers, predators, and everything else built on that energy flow. UVB can also be particularly damaging to early life stages, and many marine organisms release eggs and larvae into the water column, where exposure can be difficult to avoid. So when we imagine the ozone beginning to fail, we should not imagine only a chemical process. We should imagine recruitment faltering, productivity dipping, development going wrong, and ecosystems beginning to lose their future one vulnerable cohort at a time. There is also a cruel subtlety in the fact that the burst itself might leave very little obvious surface damage at first. A meteor impact throws dust and debris into the record. Volcanoes flood landscapes with basalt and ash. A gamma-ray burst can alter the atmosphere without leaving that sort of clear geological calling card. The world below might still look recognisably itself in the immediate aftermath. Seas would remain where they were. Sediments would continue to accumulate. Animals would continue feeding, drifting, crawling, and reproducing under conditions that no longer favoured them as they once had. The first symptom of catastrophe might not be destruction in the dramatic sense. It might be rising biological error as cells absorb more ultraviolet damage than they were built to repair. That is one reason the hypothesis is both plausible and difficult to prove. If the ozone layer began to fail because of a gamma-ray burst, the evidence would be indirect. Scientists have to infer the event from what its atmospheric consequences should look like in the biological and climatic record. Mellott and colleagues proposed the Late Ordovician extinction as a candidate because a burst could account for intense UV stress, and perhaps help trigger cooling. Thomas and colleagues modelled ozone depletion severe enough to make solar UVB a major hazard. But these ideas must still compete and interact with other explanations, especially glaciation, sea level fall, and broader climate change, which are already well supported as major features of the end Ordovician crisis. The story is not simple, yet the complexity is exactly what one would expect if atmospheric failure was part of a larger cascade rather than the sole actor on stage. A further complication comes from nitrogen dioxide, one of the atmospheric products expected after such an event. In addition to helping drive ozone chemistry, nitrogen dioxide can absorb visible light, reducing the amount of sunlight reaching the lower atmosphere and surface. Thomas's dissertation work and Mellot's climate-related modelling both noted that this could produce darkened skies and potentially contribute to global cooling. That matters because the Late Ordovician extinction is strongly associated with glaciation. A gamma-ray burst in this picture would not merely strip away ozone and increase UVB, it might also nudge the climate system toward cooling by dimming some incoming sunlight. The same atmospheric damage could therefore attack life from two sides, more ultraviolet stress above and less climatic stability overall. There is something bleakly elegant about that arrangement. First, the stratosphere becomes more transparent to dangerous ultraviolet radiation. Then, through different compounds in the same altered chemistry, the sky may become slightly dimmer in visible wavelengths. Sunlight turns both more dangerous biologically and potentially less reliable climatically. The atmosphere, which ordinarily performs the fine balancing act of making solar energy livable, becomes less competent at both tasks. It is as though the planet's environmental management department suffered a sudden collapse in staffing and decided to mishandle every incoming request at once. Life below is then left to cope not with one clear problem, but with overlapping stresses that reinforce each other. One might ask how quickly life would notice. In the strict biological sense, some effects could be rapid. Cells exposed to increased UVB do not wait politely for a committee meeting. DNA damage begins when exposure rises. Photosynthetic efficiency can decline quickly. Sensitive organisms near the surface could suffer almost immediately once ozone depletion becomes severe. But extinctions, especially on a global scale, often unfold over longer spans because ecosystems have momentum. Adult organisms may survive for some time, even if reproduction has become unreliable. Populations may continue in diminishing numbers. Food webs can absorb limited stress before they begin to break. The failure of ozone, then, is not necessarily the same as the instant of extinction. It is the beginning of a world becoming more difficult to inhabit in ways that accumulate. This delayed ecological response would have been especially significant in Ordovician seas because so much life depended on shallow marine habitats. Sea level changes later in the extinction interval would reduce those habitats anyway, but enhanced UVB could weaken them before or alongside such changes. That is why the gamma-ray burst idea is scientifically interesting, even if it never becomes the sole accepted cause. It offers a way to explain rapid atmospheric stress without a crater and provides a trigger compatible with later cooling. In other words, the day the ozone began to fail may not have been the entire disaster, but it could have been the moment the wider disaster became possible. There is another atmospheric consequence sometimes discussed in this context: nitric acid rainout. Once nitrogen compounds form in the atmosphere, they can eventually be removed by precipitation. Thomas's work noted that this nitric acid rain would likely be dilute, potentially stressful to parts of the biosphere but not necessarily catastrophic by itself, and in some contexts the added nitrate might even act as fertilizer. That mixture of harm and complication is very typical of Earth systems. Rarely does one process produce only one outcome. Atmospheric damage can cascade into effects that vary by ecosystem, geography, and timescale. A shallow marine community might suffer badly from UV stress, while some nutrient-limited environment elsewhere briefly receives a chemical gift wrapped in very inconvenient circumstances. Nature is seldom tidy. If we step back for a moment, the conceptual weight of the story becomes clearer. A burst of gamma radiation occurs perhaps thousands of light years away. The event itself is over quickly, yet on Earth, the most important immediate consequence is neither impact nor fire but chemistry. Molecules in the upper atmosphere are rearranged, ozone declines, nitrogen oxides accumulate, sunlight changes its character. A marine world that had evolved under one set of radiative conditions suddenly finds itself living under another. This is a planetary crisis delivered not through collision but through altered filtering. The sky does not fall. It stops protecting as well as it used to. That may also be why the scenario feels so unsettling. Many disasters at least announce themselves in a language living things can partly understand. Heat, noise, impact, darkness, flood. Ozone loss does not. It is atmospheric betrayal at molecular scale. The danger arrives as an increase in invisible biological damage. No Ordovician animal could have known that a distant cosmic event had changed the rates at which nucleic acids were being injured in its cells. Yet the biosphere would still feel it. There is something almost bureaucratic about the cruelty of it, like being informed that the conditions of existence have been revised and previous assumptions are no longer valid. And because the ozone layer normally works so quietly, its failure would also be easy to underestimate from our human perspective. We are inclined to respect visible structures. Mountains feel protective. Thick walls feel protective. Ozone feels almost hypothetical because it is diffuse and unseen. But the fact that something is invisible does not make it weak. A few parts per million of the right gas in the right place can decide whether shallow water ecosystems remain viable under solar radiation. The thinness of the shield is part of what makes it effective, not evidence against its importance, which means the day it began to fail would not have been a theatrical end of the world. It would have been the start of a more intimate and persistent danger, one carried in the ordinary daylight over a planet full of life not built for the new exposure. So when we imagine that day, we should not imagine a single scream from the sky. We should imagine the upper atmosphere becoming chemically unstable. We should imagine ozone concentrations falling, perhaps by severe fractions in some models. We should imagine ultraviolet B intensifying at the surface and in the sunlit ocean. We should imagine the long tail of the event, not just the sharp beginning. Because once that atmospheric protection weakens, the next stage of the story belongs to the sun and to the living world beneath it, where shallow seas, exposed plankton, vulnerable larvae, and entire marine communities would have to endure daylight that no longer played by the old rules. Once the ozone layer is badly depleted, the story stops being mainly about astrophysics and starts becoming painfully biological. A gamma-ray burst may begin the trouble, but it is sunlight that carries much of the damage into the seas and into the bodies of living things. That is what makes this stage of the scenario so unnerving. The distant event is over quickly. The sky above Earth has changed, and then the ordinary daily rise of the sun becomes part of the killing mechanism. Modelling work on gamma-ray bursts and Earth's atmosphere has consistently pointed to this as the central danger. Severe ozone loss would allow a substantial increase in UVB radiation at the surface, turning normal solar exposure into a major ecological stress. UVB is not just strong sunlight in the casual sense. It is a band of ultraviolet radiation energetic enough to damage DNA, interfere with cell division, impair photosynthesis, and injure exposed tissues. Under present conditions, the stratospheric ozone layer absorbs much of it before it reaches the lower atmosphere. When that shield is reduced, organisms that evolved under one radiation regime suddenly face another. The shift matters especially in shallow water, where sunlight penetrates readily and where many of the most productive Ordovician ecosystems were concentrated. The Late Ordovician gamma-ray burst hypothesis was proposed in part because this kind of ozone depletion would create exactly that sort of selective vulnerability. It helps here to picture the Ordovician seas not as one smooth blue emptiness, but as a layered living environment. Near the surface floated microscopic photosynthesizers and other planktonic organisms. Some spent their whole lives there. Others passed through as eggs or larvae before settling into adult habitats on the sea floor. Below them lived suspension feeders, grazers, bottom dwellers, and predators, each dependent in one way or another on the steady movement of energy down through the food web. In clear, shallow marine settings, sunlight was not merely background. It was one of the central organizing forces of life. It powered photosynthesis, helped structure productivity, and made those shelf seas unusually rich. That same dependence is what would make them so vulnerable if the character of sunlight changed. Modern observations give us a useful real-world analogy, though on a much smaller scale. Studies of the Antarctic ozone hole showed that when stratospheric ozone thinned, more UVB reached the Southern Ocean, and phytoplankton communities confined to near-surface waters became a serious concern because they are directly exposed and form the base of marine ecosystems. Smith and colleagues documented the connection between ozone depletion, increased UVB, and potential harm to surface-dwelling phytoplankton communities. That does not prove what happened in the Ordovician, of course, but it shows that the basic biological mechanism is sound. More UVB at the surface is bad news for the small photosynthetic organisms marine ecosystems rely on. Now imagine that effect amplified far beyond a seasonal polar ozone thinning and applied to a planet whose life is still overwhelmingly marine. The upper ocean becomes a more dangerous place to exist. Photosynthetic microbes are damaged more frequently than they can repair themselves. Growth slows, reproductive success falls, populations become thinner or more erratic. Some species tolerate the stress better than others, but there is no version of this story in which increased UVB is kind to the biological foundation of shallow marine ecosystems. And once the base of the system wobbles, everything built above it starts living on less secure terms. This is one reason the gamma-ray burst idea is so striking. It does not require every organism to be equally exposed. In fact, it predicts the opposite. Those most exposed to surface light should suffer most. In the original proposal linking a gamma-ray burst to the Late Ordovician extinction, Mellott and colleagues emphasized that expected severe ozone depletion would lead to intense solar ultraviolet radiation, and that some extinction and survivorship patterns from the interval could be consistent with elevated UV stress. In other words, the dying life would not be distributed randomly. The sea itself would sort the damage according to depth, habitat, and life cycle. That sorting is important because many marine organisms are most vulnerable not as adults, but during their earlier stages. Eggs and larvae often drift in the plankton, exactly where exposure to intensified UVB would be hardest to avoid. An adult animal living on or in the seafloor may appear relatively sheltered, but if its offspring must spend time in the upper water column, then a hidden bottleneck forms. Reproduction becomes less reliable. Fewer young survive to settlement. Adult populations may persist for a while, giving the illusion of resilience, but the replacement pipeline has begun to fail. This is how ecosystems can look superficially alive even while they are tipping toward collapse. Extinction is not always a dramatic mass grave all at once. Sometimes it is a long administrative shutdown of the next generation. And there is another complication. UVB does not simply burn organisms in a crude sense. It introduces cellular and developmental trouble. DNA lesions accumulate. Repair systems are taxed. Photosystems are damaged in photosynthetic organisms. Growth slows because energy must be diverted from normal function into stress response and repair. Development becomes less reliable. Some individuals live, many do not. Those that do may reproduce less effectively. Across millions upon millions of organisms, that adds up to population declines that are both biologically severe and easy to miss if one is expecting a cleaner, more theatrical disaster. The sun has not become visibly monstrous. It has become statistically cruel. In marine ecosystems, statistics are destiny. Think for a moment about a shallow Ordovician shelf. See on an ordinary day after ozone depletion has become severe. Light pours through the surface as it always has. Tiny organisms suspended near the top continue their work of photosynthesis or feeding because they have no alternative career path. Larvae drift where currents place them. Filter feeders below depend on what the upper water column provides. Nothing in the scene announces itself as impossible. Yet the ultraviolet component of that light is now more damaging. A certain percentage more cells are injured. A certain percentage more embryos fail. A certain percentage less productivity reaches the rest of the ecosystem. On one day, perhaps the losses seem small. Over seasons and generations, they become a pressure no ordinary marine community was designed to absorb indefinitely. And because the Ordovician world was so rich in shallow marine habitats, the problem could scale rapidly. This was an age of broad continental shelves and thriving epicontinental seas. Much of biodiversity was concentrated exactly where sunlight reached best. That richness, which had supported the Great Ordovician biodiversification event and all its ecological elaboration, now becomes exposure. The same architecture that made these ecosystems productive also made them open to radiative harm from above. There is something harshly ironic in that. The zones most favourable to life under ordinary sunlight become some of the most dangerous under altered sunlight. Depth, of course, offers some refuge. Water absorbs ultraviolet radiation, and deeper organisms would be less exposed than those in the uppermost layers. But refuge is not the same as safety. If near-surface productivity declines, the deeper system still feels it through reduced food supply. If larvae must rise or drift through shallower waters, depth protects adults only temporarily. If coastal and shelf environments contract later because of cooling and sea level change, deeper refuge may become ecologically disconnected from where many species can successfully reproduce or feed. So while the initial stress may be selective, the wider consequences need not remain neatly confined. The food web angle matters enormously here. Phytoplankton and other primary producers occupy a foundational role because they convert solar energy into biomass available to the rest of the ecosystem. Harm them, and one does not merely remove a species or two. One reduces the throughput of the whole system. Modern work on ozone depletion and phytoplankton has long emphasized this concern, because marine food webs are deeply dependent on surface productivity. A reduction at the base can propagate upward into zooplankton, filter feeders, grazers, and predators. Ordovician seas, though compositionally different from modern oceans, were no less dependent on this basic ecological arithmetic. There is also the issue of selectivity across geography. The increase in UVB after a major ozone loss would not affect every latitude identically, and atmospheric circulation would shape where nitrogen oxides and ozone depletion were most intense over time. But broadly speaking, sunlit low and mid-latitude shallow marine environments would be especially vulnerable simply because they combine strong sunlight with biologically rich upper waters. Mellott's proposal for a gamma-ray burst contribution to the end Ordovician extinction explicitly noted that elevated ultraviolet radiation could account for some patterns of extinction and survivorship. That is a careful way of saying the fossil record may preserve hints that exposure mattered. Now, this does not mean every death in the extinction interval must be pinned directly on UVB. That would be too simple, and Earth history is rarely so obliging. What increased radiation does is weaken systems, kill selectively, and make already stressed ecosystems less capable of coping with additional pressures. If climate cools at the same time, if sea level drops, if shelf habitats shrink, if ocean circulation changes, then populations already damaged by surface UV stress have less room to adapt. The gamma-ray burst hypothesis is scientifically interesting partly because it does not need to replace all other mechanisms. It can work as an initiating or compounding insult. The atmosphere is compromised, the seas begin to suffer, and then other Earth system changes finish what the radiation started. This compounding picture feels very plausible on biological grounds. Organisms can sometimes survive one major stressor. They are far less good at surviving several that reinforce one another. Increased UVB can reduce photosynthesis at the same time cooling alters habitats. Radiation can harm larvae while sea level fall removes nursery zones and shallow shelf communities. Surface productivity can decline just as climate instability changes circulation and nutrient delivery. None of these pressures needs to be individually perfect in order for the combined result to be devastating. Extinctions are often additive in exactly that miserable way. There is a temptation, when thinking about radiation, to imagine all affected organisms as simply dropping dead in the upper ocean like overexposed film. Real ecological damage is usually less tidy. Some species would be more tolerant. Some could avoid exposure during part of the day or season. Some might shift distribution. Some would suffer mainly in reproduction rather than adult survival. Some communities would hold together longer because food web redundancy gives temporary buffering. Others would fail quickly because they are already near their limits. The dying life, then, would not look uniform. It would look patchy, selective, and cumulative, which is exactly the sort of pattern paleontologists and extinction researchers often have to reconstruct from incomplete remains. And incomplete remains are all we ever get. The fossil record heavily favours hard parts and durable structures. It is much easier to preserve a shell than a plankton bloom. Yet the real biological centre of this problem may sit precisely in the fragile, poorly preserved parts of the biosphere. Microorganisms, soft-bodied plankton, eggs, larvae, and the everyday throughput of organic matter in shallow water. In a sense, the most important victims are also the least likely to leave a clear direct testimony. We infer their suffering from what depended on them, and from what later disappeared. Ancient disaster often speaks most loudly through absence. There is also a grimly elegant temporal structure to all this. The gamma-ray burst itself is over. The ozone layer remains depleted for years in atmospheric models of a severe event. During that time, each day of sunlight continues the assault. This means biological damage is not a singular pulse but a repeated daily pressure. Morning after morning, upper ocean life is exposed to a world that has become more dangerous. Repair systems work, fail, and work again. Productivity fluctuates downward, recruitment weakens, populations thin. The catastrophe is renewed every dawn. Thomas and colleagues' atmospheric modelling emphasise that the biological significance comes from the sustained increase in solar UVB following ozone depletion, not merely the direct initial radiation from the burst. That phrase, sustained increase, may be the heart of this chapter. Life can survive many things briefly. It struggles more with persistent shifts that make ordinary conditions harmful. Ordovician marine ecosystems evolved under a certain balance of sunlight, chemistry, and climate. Once that balance is broken, survival becomes a moving target. Species living nearest the surface face the sharpest edge first, but the rest of the system follows because ecosystems are connected whether they wish to be or not. One can almost imagine the upper ocean as a ledger slowly turning red. A little less photosynthesis, a few more failed embryos, a little more tissue damage, a little less successful recruitment, a slight change in who can survive where, then another season, another reproductive cycle, another reduction in food quality or quantity moving downward. By the time extinction is obvious in the fossil record, the real biological argument has often been underway for a long while, and all the while the sunlight itself remains visually normal enough to avoid suspicion. That is perhaps the cruelest detail. The Ordovician sun does not need to flare monstrously. It merely arrives through a damaged atmosphere. The seas gleam. The surface sparkles. Light penetrates the upper waters as always. Yet hidden within that light is a level of UVB that many organisms cannot safely absorb. Day has become more expensive than life can afford. If this chapter of the story feels intimate compared with the earlier cosmic setup, that is because it is. Gamma-ray bursts are spectacular at the astrophysical scale, but extinction is lived cell by cell, organism by organism, generation by generation. The real scene of injury is not the distant burst source. It is the sea surface, the larval drift, the photosynthesizing microbe, the shallow water community that no longer receives tolerable light. The dying life is not killed by drama. It is worn down by altered conditions delivered through the most ordinary thing in the world, daylight. Which is why the next step has to widen again from individual vulnerability to the fossil and extinction record itself, because sooner or later those daily biological losses become visible in deep time as something larger, a great thinning of marine diversity, a crisis preserved in stone, where entire groups and habitats reveal how severe the pressure became once the skies above and the seas below stopped cooperating. By the time a mass extinction reaches the fossil record, the living world has already been arguing with disaster for quite a while. That is one of the frustrating and fascinating things about deep time. Rocks preserve outcomes much more readily than they preserve the feeling of a crisis as it unfolds. They tell us who vanished, who survived, which environments emptied out, and how communities changed. But they do not give us a clean day-by-day diary of panic. The Late Ordovician extinction, sometimes called the Ordovician-Silurian extinction, was one of the largest biodiversity crises in Earth history, with roughly half of marine genera lost and perhaps around 85% of marine species eliminated. It unfolded near the end of the Ordovician, around 444 million years ago, and because almost all complex life was still marine, its record is written mainly in the seas and in the shelly remains those seas left behind. That marine emphasis matters. When we say the Great Ordovician dying, we're not talking about forests browning on land or herds collapsing across plains. There were no forests in the later sense, and terrestrial animal ecosystems had not yet arrived to complicate matters. The crisis was a marine one. Shallow shelf communities, planktonic organisms, benthic faunas, reef builders, and open water lineages all affected in different ways and at different times. The fossil record shows heavy losses among brachiopods, bryozoans, trilobites, graptolites, echinoderms, mollusks, ostracodes, and many reef-building organisms. In other words, this was not one unlucky branch of life having a difficult season. It was a broad restructuring of marine biodiversity after one of the great flourishing episodes of the Paleozoic, the Great Ordovician biodiversification event. There is also a useful corrective hidden in those numbers. Extinction percentages can make ancient worlds feel abstract, as though one is simply moving counters off a board. But each lost genus or species represents a way of living that had been established across real habitats and food webs. A brachiopod lineage disappearing is not just a taxonomic subtraction. It means a set of shell forms, feeding habits, developmental pathways, ecological roles, and geographical ranges has ended. A graptolite lineage vanishing means part of the planktonic and water column world has gone quiet. Trilobite losses are not only fewer famous fossils for museum displays, they are reductions in benthic variety across marine sediments and shelves. Extinction is always larger than a list of names, and the Late Ordovician record is full of those absences. One of the most important things paleontologists have learned about this event is that it was not a single neat pulse. It is traditionally understood as occurring in two main waves. The first coincided with the onset of major Hernantian glaciation and a sharp fall in sea level, which would have removed or compressed extensive shallow marine habitats. The second followed later in the Hernantian, during the retreat of glaciation, and is strongly associated with widespread ocean anoxia and euxenia, meaning severe oxygen depletion and, in some areas, the spread of sulfide-rich waters. So the dying was not one moment but a sequence, cooling and habitat disruption first, then a later phase tied to low oxygen marine conditions as the climate system shifted again. That two-pulse structure is important for the gamma-ray burst idea because it leaves room for layered causation. If a burst played any role, it is generally discussed as a possible trigger or contributor to the first phase, not as a complete explanation for every feature of the extinction interval. The more conventional view still places major weight on glaciation, falling sea level, and then later anoxia during deglaciation. But the burst hypothesis remains scientifically interesting because it offers a mechanism for rapid atmospheric damage and selective UV stress without requiring a crater or obvious impact debris. In other words, the fossil record does not need to testify to a single cosmic murder weapon. It may instead preserve the biological pattern of a world that became suddenly harder to live in before later Earth system stresses finished the job. If we stay with the fossils themselves, a striking feature of the extinction is how unevenly groups and habitats were affected. Brachiopods took major losses, though some lineages survived and later recovered. Graptolites, those floating colonial organisms so useful in stratigraphy, were hit hard. Trilobites also suffered significant reductions. Reef-building communities were badly affected, and some specialised faunas disappeared entirely. The Pholiomena fauna, for example, a deep-water assemblage adapted to low oxygen conditions before the extinction, appears to have vanished during the first pulse, despite having previously been widespread and relatively resistant to ordinary background extinction. That kind of selectivity reminds us that extinction events are not simply stronger versions of everyday turnover. They scramble the usual rules. At the same time, some organisms and community types manage to persist, at least temporarily, by occupying ecological or geographic refuges. During the glacial interval, a cool water brachiopod assemblage known as the Hernantia fauna spread into lower latitudes along outer shelf environments, apparently taking advantage of the new climatic conditions created by cooling. For a moment, it looked almost like a replacement regime, a cold water reshuffling of marine life rather than pure collapse. But that fauna too was later lost in the second extinction pulse and replaced by Silurian assemblages adapted to warmer post-glacial conditions. This is one of the recurring patterns in extinction and recovery. Survival is often provisional. A group can flourish in the interval between crises only to be swept away when the system shifts again. The fossils preserve this instability in layers and assemblages rather than in dramatic scenes. One bed contains a diverse community of familiar Ordovician forms. Above it, another contains reduced diversity or a different set of survivors. Elsewhere, black shales appear, signalling low oxygen marine conditions during the later Hernantian. Graptolite zones shift, brachiopod communities reorganize, certain reefal or shelf taxa disappear from the record. In some sections, the story is one of habitat loss as sea level drops and shallow environments shrink. In others, it becomes one of water chemistry turning hostile. The global pattern is broad, but the local fossil expression can vary according to paleogeography and environment. That is part of what makes paleontology both complicated and impressive. A mass extinction is one event in a loose sense, but it leaves many local biographies in stone. There is another reason the fossil record of this extinction feels especially poignant. It followed one of the great expansions of marine biodiversity. The Ordovician world had not been stagnant or impoverished before disaster struck. Quite the opposite. Marine ecosystems had become richer, more layered, and more geographically widespread during the Great Ordovician biodiversification event. Shelf communities, planktonic systems, and benthic faunas all had deepened in complexity. So the Late Ordovician extinction was not merely a pruning of a tired biosphere. It cut into a world that had recently become more elaborate and successful. The fossils therefore show us not just death, but interrupted momentum. If the gamma-ray burst hypothesis has any special appeal in this context, it is because some of the extinction selectivity looks at least compatible with increased ultraviolet stress. Mellott and colleagues argued that a nearby galactic burst could have stripped away enough ozone to expose surface-dwelling organisms and those responsible for planetary photosynthesis to severe ultraviolet radiation, and later work compared geographic patterns of late Ordovician extinction with simulations of astrophysical radiation damage. The idea is not that every fossil bed comes stamped with cosmic beam did this, but that organisms living nearest the surface or in more exposed settings might have been preferentially harmed if UV levels rose sharply after ozone depletion. That would fit a world in which sunlight had turned hostile before climate and sea level changes fully finished their work. Still, one has to be careful not to over-romance selectivity. The fossil record is selective by nature, preserving hard parts more readily than soft tissues and larger structures more readily than tiny delicate components of the plankton. Many of the most UV-sensitive victims in any such scenario, phytoplankton, eggs, larvae, and soft-bodied organisms in surface waters, would leave little direct record compared with shells or skeletons on the seafloor. Their decline would be inferred indirectly, through reduced productivity, failed recruitment, and the downstream losses of groups dependent on them. This means the great dying may have had a fragile, almost invisible front line in the upper ocean, while the fossils we collect are often the later, harder-bodied witnesses to that trouble. Absence is doing a great deal of work here. That indirectness is part of why black shales, isotopic excursions and facies changes become so important. The rocks do not simply list the dead, they preserve the environmental context of dying. The late Hernantian spread of black shales across many settings is taken as evidence for a global or near-global ocean anoxic event, the Hernantian Ocean Anoxic Event. Various geochemical proxies from multiple regions support widespread changes in ocean oxygenation during the second pulse. That matters because it helps explain why recovery after the first pulse was cut short, and why some lineages that weathered cooling and sea level fall still did not make it through the interval. Even the survivors of one disaster can be gathered back in by the next. The fossils also tell us something subtle about recovery. The End Ordovician crisis was severe, but it did not permanently erase complex marine ecosystems in the way some later extinction events did. Diversity gradually recovered through the Silurian, and in some regions, complex trophic structures reappeared relatively quickly. Harper's recent review emphasizes that although the extinction was one of the big five in magnitude, it did not produce as profound a long-term ecological reset as the End-Permian event. Silurian communities were initially simpler and broader niched in many places, yet life did rebound, and warm water benthic communities in places such as South China could become complex again surprisingly soon. That is not to minimize the severity of the extinction. It is to recognize that Earth's biosphere can be deeply wounded without being permanently reduced to rubble. There is, however, a difference between recovery and restoration. The post-extinction world was not simply the Ordovician continuing where it left off. Highly endemic faunas gave way to more cosmopolitan ones across much of the Silurian. Survivors often expanded geographically later, but the world they expanded into had changed. The Hernantia fauna had its brief moment and vanished. Some lineages never returned. Community structures reorganized around the altered climate and chemistry of the early Silurian. This is one of the quiet truths fossils preserve again and again. A mass extinction is not just a pause in biodiversity. It is a change in historical direction. Recovery does not mean going back. It means moving on from damage with whatever remains. Perhaps that is why certain fossil groups from the Ordovician carry such emotional weight, at least if one is inclined to become sentimental about shelly marine invertebrates, which I admit is a specialized form of tenderness. A brachiopod bed from before the extinction is not merely a curiosity. It is a snapshot of a marine shelf community operating under conditions that would not last. A graptolite assemblage from the right stratigraphic zone is not just a dating tool. It is a remnant of the planktonic world before the crisis tightened. A reduced diversity above the boundary, or a sudden faunal turnover in a section, is not only a data point. It is deep time evidence that marine life, after flourishing for tens of millions of years, had entered a narrowing corridor. And the corridor itself may have been narrower than a purely earthbound explanation first suggests. Traditional mechanisms remain central, and rightly so. Sea level fall would have been devastating in an age of extensive shallow shelf seas. Cooling was profound. Later anoxia was real and widespread. Yet the burst hypothesis lingers because it fits an uncomfortable truth about fossils. Sometimes they preserve the aftermath of a kind of harm that leaves no crater. If an ancient gamma ray burst contributed to the first pulse, then the fossils of the Great Ordovician dying are not only records of climate and ocean change. They are potentially the biological afterimage of a damaged ozone layer, and a period in which exposed marine life faced a sky that had become chemically less protective. The phrase left behind is apt in more than one sense. The extinction left behind shells, impressions, community changes, black shales, isotopic signals and survival patterns. It also left behind questions, Why these groups more than others? Why this timing? How much was driven by cooling, by habitat loss, by anoxia, by volcanism in some newer interpretations, and how much room remains for a short, sharp astrophysical trigger at the start? Recent debates continue over integrated mechanisms, with some researchers emphasising volcanism, warming, and anoxia for parts of the event. While the classic glaciation model remains highly influential, deep time rarely rewards single-cause simplicity. So when we look at the fossils of the Late Ordovician extinction, we are not seeing a neatly labelled autopsy. We are seeing a field of clues, communities thinned, lineages interrupted, recovery delayed, habitats transformed, and the remains of a marine world that had once seemed securely established. The great dying is preserved in brachiopods that do not return, in trilobite diversity that contracts, in graptolite records that break, in reef-building systems that falter, and in the altered sedimentary language of oceans, passing from cooling stress into suffocating low oxygen. It is one of the clearest demonstrations that a planet can lose a vast amount of life without any single dramatic scar visible from orbit. And that, in a way, brings us naturally to the aftermath, because extinction is only one part of catastrophe. What follows matters too. Once the first blow has landed and the second has deepened the wound, the world continues under altered conditions: ice, darkness, changing seas, unstable chemistry, and the long work of survival and replacement begin to define what comes next, and that is where this story now has to go. After the great thinning of life came something almost as important as the extinction itself. The world that remained had to keep going. That sounds obvious, but in deep time it is one of the most revealing parts of any crisis. Catastrophe is only the sharp edge. The longer truth lies in what happens afterward, when ecosystems try to function under altered rules, when climates shift from one extreme to another, when survivors find themselves in habitats that no longer behave as expected, and when the rock record begins storing not only the losses, but the strange new conditions under which those losses must be lived with. In the Late Ordovician, that aftermath involved ice, darkness of several different kinds, unstable seas, and a recovery that was real but uneven. The extinction itself came in two main pulses, with the first tied closely to glaciation and sea level fall, and the second associated with expanding low oxygen conditions as the climate system changed again. In other words, the world did not simply take one blow and begin healing, it staggered into a second one. The ice came first in the conventional picture, and it came on a scale large enough to reorganize coastlines and marine habitats across the globe. During the Henantian, major ice sheets expanded across Gondwana, which by then occupied high southern latitudes. This glaciation drove a substantial fall in sea level, with estimates commonly in the range of at least 50 metres and perhaps closer to 100 metres in some reconstructions. That matters enormously in an Ordovician world, because shallow epicontinental seas were among the richest habitats on Earth. When sea level falls, those broad shelf environments contract, become fragmented or disappear altogether. Entire communities lose living space, local environmental gradients sharpen, water circulation changes, what had been a broad marine neighbourhood turns into scattered remnants, and organisms adapted to particular depth ranges or substrate conditions suddenly find their world reduced. There is a temptation, when imagining glaciation, to picture only cold. Cold is certainly part of it, but for marine life, the geometry of habitat may be even more decisive. A species can sometimes tolerate cooler water better than it can tolerate the total disappearance of the broad shelf sea on which its ecology depends. The Late Ordovician was especially vulnerable to this because its biodiversity had flourished in those shallow marine settings. The very success of the Ordovician biosphere had been built on widespread continental shelves and productive sunlit waters. When the ice locked up water and sea level fell, that arrangement began to unravel. The first extinction pulse is therefore usually linked not merely to lower temperatures, but to a combination of glacial cooling and major glaciostatic habitat loss. It is one thing to ask marine life to cope with cold conditions. It is another to remove the floor plan of the ecosystem while doing so. If we place the gamma-ray burst idea alongside this more established framework, the aftermath becomes even more layered. In that scenario, the biosphere may have entered the Hernantian already stressed by atmospheric damage, increased ultraviolet exposure, and perhaps some contribution to climatic cooling through nitrogen dioxide, reducing incoming sunlight. Thomas's atmospheric modelling and the original Melot proposal both emphasise that a severe burst could deplete ozone strongly and alter atmospheric chemistry in ways that would increase biological UV stress and potentially affect climate. That would mean the ice did not arrive to a robust marine world. It arrived to one that may already have been weakened in the upper ocean and in shallow sunlit habitats, making habitat contraction and cooling harder to survive. The point is not that every part of the aftermath must be blamed on the burst, but that the long aftermath may have been shaped by a bad beginning. The darkness of this interval was not just the darkness of night or winter. It may have existed in the atmosphere, in the oceans, and eventually in the sedimentary record. If a gamma-ray burst did occur, nitrogen dioxide formed in the atmosphere would likely have absorbed some visible light, reducing the amount of sunlight reaching the surface. That would not plunge the planet into cartoon gloom, but it could dim the sky enough to matter climatically and biologically. A world already dealing with severe ozone depletion could therefore also find that the visible character of daylight had changed slightly, with less warmth reaching the lower atmosphere and surface. It is a peculiar kind of hostility, more of the dangerous ultraviolet, less of the ordinary light organisms are used to living under. The atmosphere, instead of acting as a balanced filter, begins failing in more than one direction at once. Then comes another kind of darkness, the one recorded in black shales. As the glacial phase peaked and then gave way to deglaciation, the late Hernantian and earlier Silurian saw widespread episodes of black shale deposition and evidence for expanded marine anoxia in many settings. Recent work continues to emphasise that the second pulse of the Late Ordovician mass extinction is closely associated with the expansion of anoxic marine conditions, even though the detailed extent and mechanisms remain actively studied. The broad pattern, though, is consistent. As the climate system shifted again, oxygen-poor waters became a major problem. Black shales are not just dark rocks. They are signs that organic matter accumulated under low oxygen conditions, where decomposition and circulation did not restore ordinary marine breathability. After the first pulse had reduced biodiversity through cooling and sea level fall, the second pulse hit a marine world increasingly stressed by oxygen loss. That transition from ice to anoxia is one of the most brutal features of the event. A biosphere can perhaps imagine, in a metaphorical sense, enduring one environmental regime for a while. But the Late Ordovician did not settle down into one bad climate and stay there. It moved through phases. First came cooling and major habitat disruption. Then, as deglaciation progressed and sea level rose again, many marine settings saw widespread low oxygen conditions. A species that survived by hanging on in a cool water refuge might later find that the returning seas were chemically wrong. A community that had just adjusted to shelf contraction might be met by water masses with too little oxygen. Survival became sequentially difficult in different ways. This is why the interval feels less like one disaster and more like a corridor lined with them. It is also why recovery was not immediate or simple. Some groups did exploit temporary opportunities during the glacial interval. Cool water faunas, especially the Hernantia brachiopod fauna, spread broadly during parts of the Hernantian and seem to have taken advantage of the changed climatic structure of the oceans. For a little while, this might almost look like resilience in triumph, a rapid reshuffling of marine life under new rules. But the later phase of the extinction swept many of those assemblages away as well. Harper's recent review emphasises that these Hernantian faunas were themselves short-lived and later replaced by post-extinction Silurian communities. Temporary success was not the same as secure recovery. In an extinction interval with 2 severe pulses, being suited to the first new world may only mean you are unprepared for the second one. The aftermath also stretched differently across habitats. Shallow shelf environments, already hit hard by sea level fall, later experienced the consequences of sea level rise under altered ocean chemistry. Deep water and outer shelf settings, meanwhile, often preserve the black shales and low oxygen signatures that tell us about the second pulse. There is no single universal Late Ordovician seascape that every lineage experienced in the same way. Some habitats disappeared, some reappeared transformed, some became oxygen-starved, some briefly served as refuges. For paleontologists and geochemists, this patchwork is part of the challenge. The aftermath has to be reconstructed from many local records, each preserving a different angle on the same broad crisis. One section may show hiatuses from falling sea level, another may record black shale deposition, another may preserve the turnover from one brachiopod fauna to another. Together they reveal not a steady recovery, but a world lurching through unstable states. The longness of the aftermath matters too. On human timescales, we're used to asking whether an event lasted days, months, or perhaps years. In deep time, an aftermath can occupy hundreds of thousands to millions of years. That does not mean the biosphere is in obvious visible collapse every moment of that span. It means ecological and geochemical consequences remain unresolved for a very long time. Populations rebuild slowly, geographic ranges shift, new communities establish themselves, ocean circulation and chemistry adjust, carbon burial changes, nutrient cycles change. The system does not bounce back in the cheerful elastic sense, it reorganizes. Recent geochemical work on Hernantian organic carbon burial and phosphorus cycling continues to support the idea that this interval involved major changes to Earth system feedbacks, not just a brief interruption to otherwise ordinary marine life. This is also where darkness enters in a third sense. Not simply dimmed skies or dark shales, but informational darkness for the organisms themselves. No Ordovician animal knew why the world had become less reliable. A brachiopod cannot diagnose deglacial anoxia. A trilobite cannot infer a shift in phosphorus cycling. A graptolite colony cannot hold a conference on glaciostatic stress. Life experiences aftermath as local worsening, less habitat, less oxygen, less food, more failed reproduction, more unstable distribution of suitable conditions. The scientific reconstruction gives us the planetary view, but the real aftermath was lived as countless local impossibilities. One shelf sea became too shallow, another later became too oxygen poor, another changed temperature, circulation or chemistry, just enough to push a lineage over the edge. Mass extinctions are global in summary but intimate in experience. There is some comfort, if comfort is the right word, in the fact that recovery did happen. The End Ordovician event was one of the big 5 extinctions, but it did not permanently reduce marine ecosystems to ecological rubble in the way the End Permian did. Diversity recovered through the Silurian, and some marine systems regained significant complexity relatively quickly in geological terms. Harper notes that while the extinction was severe, the long-term ecological reset was not as profound as in some later crises. Yet the recovery was not a restoration of the old Ordovician world. Early Silurian communities were often more cosmopolitan, less endemic, and reorganized around the new conditions. Recovery in this sense means history continued, not that it reversed. The old world was not repaired, a different one replaced it. Reefs illustrate this nicely. After the End Ordovician extinction, reef systems did recover, but not instantly. Evidence from later Silurian coral stromatoporoid reefs indicates that substantial global reef recovery took several million years. Reef ecosystems are complicated structures requiring multiple interacting builders and favourable environmental stability. Their delayed rebound tells us something important about the long aftermath, even when general marine diversity begins recovering. the most elaborate ecological architectures can take much longer to return. Complexity is not the first thing a wounded biosphere regains. It begins with persistence, simplification, expansion of survivors, and only later rebuilds the more intricate living frameworks. That slow rebuild makes the aftermath feel almost patient in the worst possible way. Earth does not hurry because life is upset. Ice sheets advance and retreat according to physics, not morale. Oxygen conditions shift according to circulation, productivity, and stratification, not fairness. The seas refill, black shales accumulate, refugia appear and disappear, survivors spread, only to be checked by later change. In our own lives, aftermath suggests cleanup, grief, and then some recognizable return to routine. In Earth history, aftermath can be a prolonged negotiation with a planet that has not decided what sort of world it wants to be next. The Late Ordovician was exactly that sort of negotiation, and the possibility of a gamma-ray burst at the beginning of this sequence lends the whole interval an additional chill. If that idea is right, then the long aftermath began not solely with Earth's own internal climate and tectonic processes, but with a brief astrophysical insult that damaged the atmosphere and may have nudged the system toward instability. The glaciation, sea level fall, and later anoxia remain central regardless. But the mood of the story changes if the first shove came from deep space. Then the ice and darkness are not just terrestrial consequences. They are part of a larger chain in which a distant event altered the atmosphere, weakened the biosphere, and left Earth's own systems to carry the crisis forward. The burst is brief. The aftermath belongs to the planet. There is a peculiar humility in that. Earth is not helpless, but it is permeable. It sits within larger systems and can be knocked off balance by events outside itself. Once pushed, however, the details of disaster become unmistakably earthly. Ice sheets grow over Gondwana. Sea level falls. Shelf seas contract. Carbon burial changes. Black shales spread. Oxygen vanishes from marine waters where life once flourished. Extinction pulses separate, but the wound is continuous. If the burst was the thrown stone, the ripples belong to ocean and climate for a very long time afterward. So when we picture this interval now, we should not see only the instant of danger. We should also see the age that followed it. A colder world, then a chemically harsher one. A marine biosphere reduced, reorganized, and repeatedly pressed. Dark sediments gathering in low oxygen waters. Survivors finding temporary footholds. Reefs absent or diminished. Faunas spreading, failing, and being replaced. The immediate violence may have been swift, but the true shape of the catastrophe was extended, and to understand how scientists piece together something so ancient and so indirect, we have to move from the aftermath itself to the methods that allow them to reconstruct a disaster no one witnessed. From fossils and isotopes and atmospheric models to the careful argument that such a strange chain of events might really have happened at all. What makes this story scientifically satisfying is that no one needed to witness it for it to become a serious question. Deep time almost never gives us the luxury of eyewitnesses. It gives us fragments, patterns, chemical traces, probabilities, and the occasional fossilized inconvenience. From those, scientists try to reconstruct not just what happened, but how it happened, in what order, under what conditions, and whether one proposed cause actually fits the evidence better than another. In the case of the Late Ordovician extinction and the gamma-ray burst hypothesis, that reconstruction has required a kind of scientific braid. Paleontology, stratigraphy, geochemistry, climate history, and astrophysical modelling all woven together. No single line of evidence can settle the matter by itself. The argument lives in how the strands align. The first strand is the fossil record, because that is where the biological reality of the extinction appears most plainly. Scientists began by recognising that the end of the Ordovician marks one of the major biodiversity crises in Earth history, with very large losses among marine organisms, since complex life at the time was overwhelmingly marine. Fossils from brachiopods, trilobites, graptolites, bryozoans, corals, echinoderms and other groups show that this was not a local or trivial turnover. It was broad, global and severe. The fossil record also revealed that the extinction was not one single instantaneous event, but is commonly resolved into two principal pulses, one associated with Hernantian glaciation and sea level fall, and a second associated with later oceanic anoxia during the transition out of the glacial peak. That framework came before the gamma-ray burst idea, and remains the core scaffold of the event's interpretation. Once that fossil framework was established, scientists began asking more detailed questions. Which organisms were hit hardest? Were shallow water taxa more vulnerable than deeper water ones? Did planktonic or near-surface organisms show patterns one might expect if ultraviolet stress had intensified? Did survivorship vary by latitude, habitat, or life habit? Those are exactly the sorts of questions that matter if one is considering atmospheric ozone loss as part of the crisis. A gamma-ray burst would not leave a crater, but it should leave biological selectivity. The original Mellott paper argued that severe ozone depletion from a nearby galactic burst could expose surface-dwelling organisms and those central to photosynthesis to elevated ultraviolet radiation, and that some observed extinction and survivorship patterns at the start of the event might be compatible with that sort of stress. Compatible is the key word here. The claim was not that the fossils alone prove a burst happened, but that they do not rule it out and may fit it in meaningful ways. That leads to the second strand, stratigraphy and timing. In deep time science, it is not enough to say two things happened in roughly the same era. You need to know whether they line up closely enough to support a causal chain. Researchers use fossil zones, sedimentary sequences, isotope excursions, and regional correlation between rock sections to establish the sequence of events as precisely as the record allows. For the Late Ordovician extinction, this work has shown that the first pulse is closely tied to the onset of glaciation and sea level fall, while the second pulse lines up with widespread marine oxygen stress and black shale deposition in many sections. That chronology matters because any astrophysical trigger would have to fit at the front end of the sequence. It would need to explain, or at least plausibly precede, the initial biological crisis, not merely be dramatic in the abstract. The third strand is geochemistry, which is often where Earth history becomes both more rigorous and less glamorous. Fossils tell you who was there and who disappeared. Geochemistry tells you what kind of world those organisms were living in. Scientists measure carbon isotopes, sulfur signals, trace metals, sediment colour and composition, and other proxies to infer oxygenation, productivity, climate change, and shifts in the carbon cycle. In the Late Ordovician record, geochemical evidence has supported major climate change, glaciation, sea level fluctuations, and, for the second pulse especially, expanded marine anoxia and euxenia in some settings. More recent work has also explored volcanic drivers and linked volcanic activity, warming or cooling pathways, carbon cycle disruption, and later ocean chemistry to the extinction interval. This matters because the gamma-ray burst idea enters an already busy field. Any new hypothesis has to compete with or complement explanations already grounded in robust geochemical evidence. So how do scientists test a gamma-ray burst scenario if no direct physical remnant of the burst is expected in the rocks? This is where the fourth strand comes in. Atmospheric and astrophysical modelling. Researchers do not start by looking for a magic fossil that says space did this. They begin with known physics. Gamma-ray bursts are real, observed astrophysical phenomena. Their energies, durations, and beaming properties can be estimated from modern astronomy. From there, modellers ask what would happen if Earth were exposed to a burst of a given intensity from a plausible galactic distance. Thomas and colleagues modelled the atmospheric consequences and found that a burst within the Milky Way could cause severe ozone depletion by ionising the atmosphere and generating nitrogen oxides that catalytically destroy ozone. Those models then translate into biological implications because reduced ozone means much higher UVB exposure at the surface. This modelling step is critical because it ties the space event to Earth systems quantitatively rather than rhetorically. Without it, the hypothesis would remain a colourful story. With it, scientists can estimate how much ozone might be lost, how long recovery might take, how much UVB might increase, and whether such changes are severe enough to plausibly stress a marine biosphere. Thomas's dissertation work and later atmospheric studies explored not just ozone depletion, but also related chemistry such as nitrogen dioxide production, which could reduce visible sunlight somewhat and potentially contribute to cooling. Mellott and colleagues extended this to climatic and biogeochemical effects, arguing that the atmospheric aftermath of a galactic burst could, in principle, fit aspects of the Late Ordovician crisis. These papers do not prove the burst happened. They establish that the mechanism is physically credible and biologically serious. From there, scientists compare the modelled consequences against the paleontological and geological record. This is where reconstruction becomes a detective story rather than a calculation exercise. If severe ozone depletion occurred, one would expect enhanced ultraviolet stress to affect organisms in shallow or surface-exposed environments, more than deeply buried or deep water forms. One might expect planktonic systems and larval stages to be especially vulnerable. One might also expect a strong event to occur abruptly enough to explain a rapid onset of stress without an impact crater. The original GRB papers and subsequent discussions emphasised these kinds of predicted patterns and compared them with known late Ordovician extinction selectivity. Again, the point is not that the fossils speak with one voice, but that the fossil and model patterns can be laid against one another to see whether they align. There is an important caution here, and good scientists tend to dwell on it. Pattern matching is useful, but it is not the same as proof. Many causes can produce overlapping biological signals. Shallow water taxa may be vulnerable not only because of UV stress, but because shallow shelves disappear when sea level falls. Plankton may suffer for reasons related to climate, circulation, nutrients, or oxygenation, not just ultraviolet damage. This is why the gamma-ray burst hypothesis remains a hypothesis. It is physically plausible and consistent with some features of the extinction, but it is not uniquely required by the current evidence. The late Ordovician extinction can be powerfully explained by glaciation, sea level change, and later anoxia even without a burst. The burst idea survives because it may help explain how the crisis began so sharply, and why some exposure-related patterns are interesting, not because the rest of the evidence has been discarded. That brings us to a fifth strand in the reconstruction: comparative plausibility. Scientists do not evaluate hypotheses in isolation. They ask whether one explanation accounts for more of the evidence than another, whether multiple explanations can work together, and what sort of evidence would discriminate among them. In recent years, some work has argued for a stronger volcanic role in the late Ordovician crisis, using mercury spikes and other proxies to suggest intense volcanism as a trigger for climatic and environmental disruption. Other recent reviews point to volcanism as a possible ultimate cause behind both the extinction and the associated ice age. That means the gamma-ray burst hypothesis is now part of a more crowded explanatory landscape than when it was first proposed. Reconstructing the catastrophe, then, is not a matter of choosing between space and Earth in some theatrical contest. It is a matter of asking whether the event was driven by one dominant mechanism, several overlapping ones, or a trigger-plus feedback sequence in which an initial insult pushed Earth systems into further instability. One reason the GRB idea still attracts attention is that it neatly explains something many geologists dislike having to explain without a trigger: why a major extinction and climatic transition might begin abruptly without leaving an obvious impact scar. A gamma-ray burst would be effectively invisible in the ordinary geological sense. It would not deposit exotic debris or excavate a basin. It would act through atmospheric chemistry. That makes it frustrating to confirm directly, but also attractive where the record seems to suggest fast atmospheric, biological disruption without a crater. Scientists are accustomed to such asymmetries. The Earth does not owe us convenient evidence. Sometimes the most important causes are the ones that leave only indirect fingerprints. Another major tool in this reconstruction is simulation beyond the atmosphere itself. Researchers have modelled not only ozone depletion, but downstream biological and even oceanic consequences. The broader gamma-ray bursts in the Earth. Work explored atmospheric, biological, climatic, and biogeochemical effects in a more integrated way, asking what a burst would do across the whole Earth system. More recent work has even modelled the effects of a galactic gamma-ray burst on ocean plankton, because plankton are a particularly sensitive and globally important part of marine biospheres. These studies do not reconstruct the Ordovician directly by themselves, but they sharpen the biological plausibility of the mechanism by showing what kinds of damage to expect in marine primary producers and surface ecosystems. At the same time, paleontologists and geochemists continue refining the Late Ordovician event itself. Better age constraints, more regional sections, improved isotope records, and larger fossil databases all make the reconstruction sharper. Recent reviews emphasise how much better we now understand the two-pulse nature of the extinction, the links to the Hernantian Ice Age, and the later spread of low-oxygen conditions. The more precise that Earthside reconstruction becomes, the better we can test any external trigger. If extinction onset proves highly synchronous in a way that fits a rapid atmospheric insult, that helps the GRB scenario. If timing and selectivity line up better with slower Earthbound forcing, that weighs against it. Reconstruction is therefore not a one-time act. It keeps improving as every side of the evidence base gets better. One of the more elegant aspects of this scientific process is that it relies on the independence of different methods. Fossils do not know what the atmosphere models say. Atmosphere models do not care what the rocks want. Astronomers studying gamma-ray bursts are not secretly adjusting neutron star mergers to flatter brachiopods. Each line of evidence comes with its own methods, uncertainties, and standards. That independence is exactly what gives the reconstruction power. When several lines point in compatible directions, confidence rises. When they do not, the hypothesis weakens or becomes more nuanced. Science here behaves less like a courtroom drama and more like triangulation in fog. No one point gives you the whole landscape, but enough angles begin to define the shape. There are, of course, limits. We do not have a direct gamma-ray burst marker horizon in Ordovician rocks. We do not have a fossilised trilobite holding a note that says the sunlight has become biologically unreasonable. We infer, we compare, we model, and we remain honest about uncertainty. That honesty is a strength, not a weakness. The best version of this reconstruction is not scientists proved beyond doubt that a gamma-ray burst caused the extinction. The best version is that scientists reconstructed a major marine extinction in detail, understood its climatic and oceanographic phases, recognised that some parts of its onset might be compatible with a sudden atmospheric insult, and then tested whether a known astrophysical phenomenon could plausibly provide that insult. That is real progress, even if the final answer remains open. In a way, the whole exercise is a good example of how science handles events too large, too old, and too indirect for any straightforward narrative. It begins with observations. Fossils vanish, sediments change, isotopes shift. It moves to mechanisms. Glaciation lowers sea level, anoxia spreads, volcanism may perturb climate, a gamma-ray burst could destroy ozone. Then it asks which mechanisms fit which observations, in what sequence, and with what predictive power. The result is not a tidy storybook certainty. It is a ranked landscape of explanations. Some are strongly established, like the central roles of glaciation, and later, anoxia. Some are plausible and provocative, like the gamma-ray burst trigger. Some gain or lose strength as new data arrive. Reconstruction is therefore not just about solving a mystery. It is about keeping the mystery in contact with the evidence as both improve. There's also something quietly moving about the fact that this reconstruction depends so much on leftovers. A shell bed, a black shale, a carbon isotope excursion, a modelled jet from a collapsed star, a paper comparing extinction geography to UV damage predictions. None of these is dramatic on its own, yet together they allow us to reason our way back toward a world with no witnesses and no memory except what matter retained. Scientists reconstructed this catastrophe not by finding one perfect clue, but by accepting that ancient reality is usually distributed across many imperfect ones. And perhaps that is why this part of the story feels so satisfying after all the ice, radiation, and dying life. The catastrophe itself may have been indifferent, but the reconstruction is anything but. It is patient, skeptical, cumulative work. It turns scattered traces into sequence, mechanism, and possibility. It does not restore the lost world, but it lets us see how much can be learned from what remains, which naturally leads to one final question, and perhaps the most human one of all. What a story like this says about our own world now, still alive under a protective atmosphere, still orbiting under the same galaxy, and still depending perhaps more than we care to admit on a very thin margin between ordinary daylight and something far less forgiving. We still live under the same basic arrangement that made the Ordovician world possible and vulnerable all at once. There is a planet with oceans, a thin atmosphere, a star generous enough to power life and dangerous enough to require filtering, and above that atmosphere a galaxy carrying on with its own business. The details have changed, of course. Our continents are in different places. The seas host different organisms. Forests now cover land that was once bare, and one particularly restless primate now builds observatories, satellites, and comment sections. But the larger truth has not changed. Earth is not outside the universe. It is inside it, and life depends on a remarkably narrow set of conditions holding together at the same time. The Late Ordovician extinction remains one of the clearest examples of how large-scale environmental disruption can remove a great share of marine diversity, and the gamma-ray burst idea remains scientifically interesting, because it asks whether part of that disruption may have begun with a brief astrophysical insult that damaged the atmosphere before more familiar Earth system stresses took over. That is part of what deep time says about fragility. It does not say that life is weak in any simple sense. Life on Earth is in fact annoyingly persistent. It has survived asteroid impacts, volcanic crises, glaciations, oxygenation shifts, continental rearrangements, and extinctions severe enough to rewrite the cast list of the biosphere. The Late Ordovician event itself, despite removing a huge fraction of marine biodiversity, did not end complex life, and recovery followed in the Silurian, even though the rebuilt world was not simply a restored copy of the old one. Fragility, then, is not the opposite of resilience. The two sit together. A biosphere can be resilient over millions of years and still be vulnerable to certain thresholds, certain combinations of stresses, and certain changes in climate, chemistry, or radiation that arrive too fast or too broadly for adaptation to manage. There is also a humbling lesson in the mechanism itself. If the burst hypothesis is even partly right, then one of the most dangerous features of the event was not direct destruction, but the failure of a protective system so quiet that most organisms would never have noticed it as a distinct thing. Thomas and colleagues' modelling showed that a burst within a few kiloparsecs could severely deplete ozone and raise biologically harmful UVB at the surface, while related work explored how nitrogen dioxide and other atmospheric products could also alter climate and biogeochemical conditions for years. That is a useful reminder that safety on Earth often depends on layers we do not perceive directly. The ozone layer is not dramatic. Atmospheric composition is not emotionally persuasive on its own. Yet change those invisible layers enough and the terms of life alter quickly. Human beings, for all our technology, remain just as dependent on atmospheric stability as any earlier organism. We have simply become articulate enough to describe the dependency while continuing to test it in creative ways. Another lesson is that causation in nature is often stacked rather than solitary. The current mainstream understanding of the Late Ordovician crisis still centres on glaciation, sea level fall, and later ocean anoxia, with recent work also continuing to evaluate volcanic contributions and Earth system feedbacks. The gamma-ray burst hypothesis has not replaced that framework, and it would be misleading to present it as settled fact. Its real value is that it teaches us to think in chains. A distant event may damage the atmosphere. Ozone loss may increase UV stress. Atmospheric products may also alter incoming sunlight and climate. Marine ecosystems may then become more vulnerable, just as glaciation removes habitat and later ocean chemistry turns more hostile. Catastrophe, in other words, is often cumulative. The world does not always fall apart because of one perfect blow. Sometimes it is weakened in one place, pressed in another, and finally broken in a third. That way of thinking matters very much in the present. Even though the specific risk from a gamma-ray burst right now appears low, the broader astrophysical literature treats nearby well-aimed long gamma-ray bursts as rare on human timescales, and work on galactic habitability and GRB rates generally frames them as deep time hazards rather than immediate practical threats. Still, rare is not the same thing as irrelevant when one is talking about hundreds of millions or billions of years, which is why astrobiologists and astronomers continue to study them as one of several possible cosmic influences on planetary habitability. The useful point for us is not to become melodramatic about tomorrow night's sky. It is to understand that the habitability of a planet depends on both internal stability and external luck. Earth has had both often enough for us to exist, but deep time makes clear that neither should be mistaken for a permanent entitlement. There is, I think, a quieter and more personal lesson too. We tend to imagine fragility as something obvious, a cracked shell, a failing heart, a coastline eroding under a storm. But at the planetary level, fragility can mean reliance on consistency. The Ordovician seas were full of life because sunlight, atmosphere, ocean chemistry and habitat structure had remained within ranges that allowed ecosystems to become rich and elaborate. Once those ranges shifted sharply, especially in overlapping ways, abundance became exposure. The same shallow seas that supported extraordinary diversification also became vulnerable to sea level fall and, in the burst scenario, to enhanced ultraviolet stress. There is something deeply recognizable in that. The systems that nourish us are often the ones whose disruption hurts most. What sustains life is not merely energy or matter in the abstract, but the reliable arrangement of conditions. Disturb the arrangement, and the same world becomes hard to inhabit. Deep time also has a way of correcting human vanity without requiring us to feel pointless. The Ordovician extinction, whether or not a burst helped initiate it, reminds us that life's history has never depended solely on intelligence, intention, or deservingness. No marine invertebrate of that age did anything wrong. No shallow water community caused a gamma-ray jet, a glacial onset, or an anoxic ocean. The biosphere was simply exposed to a chain of conditions larger than itself. That can sound bleak, but it is also clarifying. It means that humility is not a moral pose. It is a factual response to scale. At the same time, unlike Ordovician brachiopods or trilobites, we do have the ability to study threats, model atmospheric change, detect high-energy events, and understand the dependence of life on planetary systems. Knowledge does not exempt us from vulnerability, but it does alter the terms of responsibility. That responsibility is not mainly about gamma-ray bursts, to be clear. The greater practical relevance for us lies in the principle rather than the specific event. We now know from atmospheric science, paleontology and climate research that relatively thin and chemically subtle layers of the Earth system can carry enormous biological importance. We know that biodiversity can flourish for tens of millions of years and still be cut back hard when multiple stressors converge. We know that recovery after mass extinction is measured in geological time, not election cycles or quarterly reports. And we know that the atmosphere above us is not scenery. It is a working condition of life. The Ordovician story, even in its most speculative gamma-ray burst version, reinforces all of that. It tells us that planetary habitability is not a permanent possession, but an active state maintained by balance. Perhaps that is why this story feels oddly intimate despite its scale. A dying star or merging neutron stars somewhere in the galaxy is almost too large and distant to feel real in emotional terms. But ozone, sunlight, shallow water, failed larvae, altered food webs, cooling, black shales, and the slow return of complexity after a crisis, those things are graspable. They bring the cosmic down into the breathable. They remind us that life does not experience the universe in grand abstractions. It experiences it through conditions. How much radiation reaches the surface, how much oxygen is in the water, whether habitats persist, whether reproduction still works, whether the next generation survives. The same sky that inspires poetry is also a machine for delivering energy. And the atmosphere is what keeps that delivery within tolerable bounds. There is something almost comforting, oddly enough, in the fact that scientists can reconstruct so much of this at all. No one witnessed the Late Ordovician dying. No voice carried through from those seas to tell us that the light had become harsher, or the water less forgiving. Yet by combining fossils, stratigraphy, geochemistry, and atmospheric modelling, researchers have been able to outline one of the most consequential crises in marine history and test even highly unusual hypotheses about how it may have started. That does not remove uncertainty, but it does show that the world is not wholly opaque to careful attention. Deep time keeps its secrets, yes, but not perfectly. Matter remembers enough for us to learn humility from it. So under the same sky, what does this ancient event finally say? It says that our world is durable but not invulnerable. It says that life can be both persistent and precarious. It says that the atmosphere is a thin mercy rather than an afterthought. It says that crises often begin before they are visible and that their causes may come from several directions at once. It says that the galaxy is mostly not interested in us, which is good but not the same as being irrelevant to us. And it says that every stable evening under a breathable sky is the result of balances held in place at scales from the molecular to the cosmic. That is not a reason for panic. It is a reason for attention. And now, after all this talk of ancient oceans, violent stars, wounded atmospheres, black shales, and the long patience of recovery, here we are again in the present, a little farther along than when we began, though perhaps not by as much as the clock claims. Somewhere above you, the stratosphere is doing its quiet work. Far beyond it, the galaxy continues with its extravagant habits. Most of tonight's light is ordinary. Most of the sky is mercifully uneventful. If there is any calm to be taken from this story, perhaps it is this. Fragility is not only a warning, it is also a way of noticing what has to go right for life to feel normal. And normal on a planet like this, beneath a sky like this, is already a remarkable thing.